Друзья, всем привет! Меня зовут Глазков Андрей, я занимаюсь сетевой инфраструктурой в Яндекс.Облаке.
Hello, my name is Andrei Gleskov, and today I will be your moderator and I will be your advocate for our speakers. Today, actually, we're holding this conference online, and I think that you have noticed that some of the speakers are present here at these premises, and most of us will join us by Zoom. We're very grateful for you to joining us today, that you are motivating us to make our next hub conference even more interesting, selecting unique technical content. So take your seats, sit cozy in your chairs, and welcome, follow me. And now, some of the housekeeping issues. So there are two broadcasting available, Russian channel and English channel. You're invited to choose the one which you like most. The program of the conference is available through the link which you may find on our website. There will be 13 presentations broken down by 4 sections, 2 hours each. Between them, we'll have 30 minutes breaks. Also, we'll try to leave a little bit more than 5 minutes for your Q&A. You're invited to ask your questions on our Telegram chat, the link you may find below. If you want your question to be asked aloud, use hashtag question. So next hub conference stands open. And our very first presentation will be delivered by Alexander Azimov, who is an expert from Yandex, who is dealing with the questions related to BGP, security, and other monitoring things. He will tell us about the future of the networks which are dubbed self-healing. So, is it true that network engineers are no longer useful? Over to you. Some moment of hesitation when you do not know what button to push and no one is there to help you. Hi everyone, my name is, as Andrei has introduced me, Alexander Azimov. I'm doing some monitoring and transport infrastructure for Yandex, and today I will tell you how to make unique features for your network. In case there are some spine problems, this network could heal itself. And what role the label will play, for those who do not know, I will give a detailed introduction for many network engineers. Data center network starts with store, with the rack. Usually, TOR has actually connection to the spines. These connections usually are deemed equal, and between the uplinks, actually you will use hash in order to balance it, including Qrator and different IPs. So there are no surprises there. Then let me speak about the architecture of labels. So the spines of the first level are not connected between themselves and actually are connected by means of superspines. And X will stand for superspine, just for practical purposes. And it's obvious that, on the other hand, we have TOR connected to the spines of the first tier, and what is so important about that picture? If we have interaction within the rack, then interaction is done through TOR. If the interaction goes within the module, then it goes through the spines of the first tier. If the interaction goes between the modules, then we have TOR number 2, and that means that actually the interaction will go through the tier 1 and tier 2. Academically or theoretically, such an architecture is very much scalable once you have port capacity. If you have some empty room in data center and fiber optics, you can increase the number of tiers and increase the overall capacity of the network. Actually, it's very easy to be done on paper. I will not speak in more detail about that. So I'd like to make right conclusions. We have one data center and many routes which are independent. One route actually is available only within TOR. Within the module, the number of paths equals the number of planes. Between the modules, the number of paths equals super spines multiplied by the number of spines. And to make it easy for you to feel the scale, I will give you the figures which are true for the data center. So there are 8 planes with 32 spines within each. So it means that we have 256 intermodular interactions. If we develop a data center, a failure-free data center, a self-healing data center, then the plane architecture is the right way to do. Because therefore you can address the scalability problem, and there are multiple independent paths, and the question remains how such an architecture may live through the failures. They might be different failures, so this is what we're going to discuss. But for instance, one of the super spines has failed, and I will get back to the double plane architecture because it would be easier for us to understand what is going on. X11 is ill. How will it affect the services which are living within the data center? A lot would depend on how the failure looks like. For instance, if it's a good and profound healer, so actually if this failure can be captured by the automatics, and if the automatics would isolate the nodes, then the traffic will be rerouted to the alternative path, and the services will not notice anything. This is the best case scenario. The bad case scenario is when we have losses and when the automation doesn't notice the problem. In order to understand how it may affect applications, we'll have to spend time on looking at how TCP protocol works. I think that I will not shock anyone that TCP, this is when the transmission is acknowledged or confirmed. So the sender sends 2 packages and would get a cumulative act that I have received 2 packages. After that, actually, the sender sends 2 packages more, and the situation would replicate. So this is with a little bit of simplification. So the scenario is true once the number of packages equals 2. On the fly, I mean. And we'll continue to speak about the resending of packages, but in essence, the window doesn't affect it. What will happen if we have lost package number 3? So in that case, so the receiver will get the packages number 1, 2, and 4, and using SIK option, he will inform the sender that 3 packages were received and number 3 is lost. And the sender, at that moment of time, with no problem, will repeat sending of the lost package. But once the lost package is lost, number 4, the situation would be totally different. The receiver will receive the first 3 packages and actually would start reading immediately through the optimization of TCP format. He will not anticipate the final package once there is no notification that there should be 4 packages. And after some time waited, he will send a notification of the receipt of 3 packages, and the sender will also wait until the 4th package is delivered and not to overload the network. He will wait until the system actually informs him that something is lost. RTO stands for certain constant figures. What is important that if we are unlucky and the 4th package is lost once again, then RTO would double. So every failed attempt doubles the RTO. So let's look at how RTO looks like. By default, the minimum RTO equals 200 milliseconds. And this is a minimum RTO for data packages. For scene packages, it equals 1 second. You may see that the very first attempt to resend the package will take 100 times more than the RTT time within data center. Let's get back to our scenario. What happens within the service? The service is losing the packages. So initially, it is lucky enough that something is lost within the window. It would get a SAC and would confirm or resend the packages which were lost on the way. But if the unlucky cycle goes on, the RTO takes place. And what is so important there? Really, we have a lot of paths within the way, but PTC traffic will go through the same failed stack. So it means that under the condition that X11 is not healing itself, will not result in rerouting of the traffic. We'll try to deliver the package through the same failed node, and it will actually result in a domino effect. There will be a lot of interacting applications and a number of TCP connections. Almost all the applications available from the data center would erode, and following the proverb that actually once you fail to put the shoe on the horse stumbles, and once the horse stumbles, you lose the war. And this erosion, which affects the services, means that the users will fail to receive all the information, and the retention time would increase. There are two classical solutions, textbook solutions. First of all, this is about services. The services which try to be on the safe side and solve the problem by means of mending the TCP stacks, or make timeout at the level of the application, or make TCP sessions reuse with software-defined health checks. But the problem is that such solutions are not scalable at all, and B, they are not checked and verified. So if certain service by chance would actually configure the options and applications the way actually it's good, it would not be applicable to all the applications and for all the data centers. And secondly, the service will not understand what was done correct and what was done not correct. So it was done poorly and not scalable. If a network problem arises, who is to be blamed for that? Certainly it would be NOC to be blamed for that. What NOC does? Well, at least many services believe that the work is done like that within the NOC, but frankly speaking, this is only a part of the approach. NOC, according to the classical way, also does a lot of monitorings, black box monitoring, white box monitoring. Black box monitoring was dwelt on by Alexander Klimenko at the previous Next Hop. But he used a spine as an example. But an ideal monitoring will have certain time lag, usually several minutes. After, actually, it turns on, the network engineers will take time in order to recheck everything, localize the problem, and somehow solve the problem. So the healing will take 5 minutes in best case scenario, or in worst case scenario, actually it will take about 20 minutes. Obviously, all that time, 5 to 20 minutes, will have service degradation, which probably is no good. And something which we would like to get is that we have so many paths, and the problem arises because TCP flows use the same path, and we need something in order to use multiple paths within one TCP connection. Similarly, we have a solution. We have TCP, which is called multipath TCP, but it was developed for a totally different purpose. It was designed for iPhones. I apologize. For smartphones, not for iPhones, sadly, which have several network devices. And in order to maximize the data transmission or to make a primary backup regimen, a mechanism was designed which is absolutely transparent for applications, creates multiple paths, and in case of a failure, you may switch between them and optimize the band. But there are some nuances. In order to understand these nuances, we'll have to look at how the flows work. So the flows are structured hop by hop. And here a problem arises. If the first flow doesn't install well, the flow number 2 and number 3 will never be installed, will never merge. So it means that multiple TCP does not address the problem of failure of the first flow. So if actually the first flow goes down, the multiple TCP turns into ordinary TCP, and therefore we cannot take advantage of the multiple paths. What can help us? Some of you probably have already guessed that an important role would be played by IPv6 header. Actually, it is not available within v4. It takes 20 bits. And there were some debates about how to use that properly. So the debates were going on, something would be recorded, and Linux Nucleus did something which is off record, and will tell you what was done. But to begin with, let us do a little bit of investigation, and we'll tell you what was done to Linux nuclei within several years. 2014, an engineer from one big and respectful company adds a dependence of low label on socket hash. So what they try to mend, this is actually has something to do with RFC 6438. Very often within the nucleus, we encapsulate IPv6 and IPv4. And for some time, there were problems with switches which could not look into two headers in order to get to TCP or EDP and to find appropriate ports. And it turned out that hash, if you look at the first two IP headers, they are fixed. In order to avoid that, in order not to jeopardize the balancing, they suggested to use hash of 52PL into the header. The same was done for other encapsulation schemes for UTP. This way or another way, the purpose was quite obvious, and it was quite useful exercise for that period of time. In 2015, the same engineer actually offered a new patch, and it looked very interesting. So it says that we will randomize hash in case of negative event on the route. What a negative routing event is? This is RTO, which we have discussed before. This is a loss of the window host, and the event is really very negative. And it would be quite difficult to guess that it is what caused the failure. 2016, another esteemed company, a big one actually, collects the lost scratches and makes sure that this hash, which we have randomized now, is retransmits on every sync ACK. And the final objective is to make sure that the traffic, in case of losses, overloading of connections, could reroute.
Of course, after that, there have been many publications that you can find easily. Well, actually, you can't find them because there has been no publication on their subject at all. But you already know a solution. If you haven't fully understood what has been done, I will tell you now. To conclude about what has been done, what functions have been added to the Linux core. SKTX hash is randomly changed after RTO. That's the negative result of routing. The hash depends on this TX hash, and the flow label depends on the backhash or the SKB hash. There are some functions here which I couldn't actually put on this slide, but you can check them later. What is important here is the value of the flow label field, which has a random meaning, and as a result, this influences our unhappy TCP flow. If there is a SAC, then we can't do anything. We are trying to resend this message, but right now it's okay. But in case of RTO, and given that we added the flow label function, the traffic can go via another route. And the more nodes we have, the more likely it is that there will be no problem because of a failure of a particular device. There's just one problem remaining, RTO. Of course, we can't find another route, but we spent too much time on this. 250 milliseconds is too much. I told you about timeouts. Actually, 1 second of timeout is too much for a server. It can make it fail. And given that the real RTT is about 1 millisecond, 200 milliseconds is too much. So how can we reduce RTO timeouts? There are timeouts that are responsible for RTO if data is lost, but we can recover it because there is the IP function, and one of its parameters has this RTO min. Of course, we shouldn't amend the RTO on a global scale, but only locally. So this is a working mechanism. But scene RTO is harder to improve because it's like nailed there to a certain place. So it's very difficult to change it, but there is one way. We can use the eBPF. To put it simply, eBPF are small C software products which can be installed on laptops as stacks and CP stacks. And with them, it is possible to change a lot of settings. Actually, it's a long-term trend. Instead of dividing the IP function into many different parameters, we can shift towards eBPF. And by means of eBPF, we can actually amend the congestion control or other settings of TCP, various settings. But what is important is that we can use this function to change scene RTO. And you can see a link here. It is open information. And this is a working example, a very rough one, but it means that within this data center, we compare the first 44 bits. So if the IP addresses coincide, then it's OK, and we don't change the value of scene RTO timeout. Of course, we could do the same thing more elegantly. This is just an example, which is pretty simple. What do we already know? We know that this architecture is scalable. It is extremely useful if we switch flow label on the TOR, and if we have the possibility to avoid the problem sections in order to decrease RTO and scene RTO. It's the easiest way to use eBPF software. But there is a question. Is it safe to use a label for balancing? And actually, there are some fine points here. For example, you have a service in your network. Unfortunately, I don't have the time to explain what unicast means. But unicast is a server which is actually located on different servers. And there might be a problem because there is an RTO event which can arise not only when traffic goes via the factory, but this problem can also arise on the TRO buffer or on the host. And in this case, we have an RTO event, and it changes the flow label. And in this case, the traffic can go to another unicast. And if it's a stateful unicast, it's in a particular connection state. Maybe there is a particular server, and there is a problem there. Because after the RTO, the connection goes to a server which doesn't know anything about this connection. If we don't have any advanced servers or cast servers, then this traffic will just fail and the connection will break. So what can we do here? Within your controlled environment, where you do the flow label balancing, it is necessary to fix the flow label value when you go to EK servers. You can use it with the same eBPF software. But the important thing is that it needs to be done. But what can you do if you are not a data center operator, if you are a communications operator? It's also your problem, because starting with some versions, Juniper and Arista, for some unknown reason, put the default function of the flow label. As a result, you will disconnect the TCP of users using your network. So I recommend you strongly to check the settings of your system. Well, anyway, I think all of you are ready to listen to how it actually works. After we got the flow label on TORs and we prepared an agent which now lives on hosts, we decided not to wait for the next default, and we took a TOR with 4 uplinks. And we did a drop on one of them. And actually, we made it lose all the packages. And you can see that on the left, we have the first package monitoring, which went down to 75%, because 25% of the packages are lost. On the right, you can see the charts for servers that are after this TOR. They are connected within the rack, and you can see that they went even lower. Why? Why did they drop even more than by 25%? In some cases, it's by 3 or 4 times. These are those application timeouts with this unhappy connection. We try to send the data through, and the whole system is waiting for a response within this data center. And we sent a request to a number of sources, and we are waiting for them to send some information, and the system is idle. It's really bad. And now we are having the same experiment, but with the flow label value on. As you can see on the left, our package monitoring dropped by the same 25%, which is logical because this system just calculates the number of packages delivered and lost. And on the right, we have the service chart, and here you will not see the effect from the problem stack, which means that within milliseconds, the traffic flowed from the problem part to the 3 remaining uplinks, which are unaffected. And as a result, we have a self-healing network. Well, that was my last slide, and now I would draw some conclusions. I hope that right now you know how to build a data center network which is self-healing. And for that, you will not need to go to the archive of a Linux core to look for patches there. Flow label is a solution here, but we need to be careful about it. I emphasize once again, if you are a network operator, you should not use it as a hash function, because then you will disrupt your user's session. There is a conceptual switch that network engineers should do. They should understand that it all starts not with TOR, but with the host. And then we need to change the RTO towards unicast servers. I think it's a good example showing why it is. It all starts with the host and not with the network device. And the mechanics of the flow label is working for other administrative segments, such as the RTC traffic, and we can use it in order to control the outgoing traffic, but this is what I'm going to tell you next time. Thank you very much. If there are any questions, I am ready to answer them. Thank you very much, Alexander. That's been a very interesting presentation. Actually, we need network engineers to control the hosts. Unfortunately, we don't have any time for any questions. But Alexander, will you please answer the questions in the chat? And we are going to move further, and our next speaker is Alexander Bespalo from the company Arista. He has more than 20 years of experience in telecom, and he will tell us about the Inband telemetry and what's been there over the past years. Regarding telemetry, please look up our presentation from last year. We have a presentation from Alexander Klimenko, which is also very interesting and which completely covers this topic. Alexander, you have the floor. Good morning, colleagues. I hope you can hear me. My name is Alexander Bespalo. I am a system engineer at Arista. And today I have some slides regarding the in-band telemetry technology. This is my agenda for today. We will look into the options of in-band telemetry for today. We will look at those options that are being discussed now and that exist as drafts. And I would like to draw your attention to the fact that you should not treat this presentation as a roadmap from Arista. Our target here was to introduce new technologies of telemetry to you. Depending on the client's needs, these options will probably be implemented in the equipment. But right now, I would like to tell you about new technologies that are being discussed and that exist as draft solutions. Right now, let's see how a modern data center is functioning. It uses a lot of topology, a multitude of levels, plenty of parallel paths. Alexander tried to calculate those paths. There are a lot of them. And we can have dynamic distribution of the traffic on each level. What do we have in terms of telemetry today? All the equipment is ready to stream telemetry and export the status in the network. It's also ready to export the counters and events. But very often we would like to have more information. And we started thinking about how to get information about the real path that a certain flow of data went through, because we have lots of parallel paths in our data center. So in what section, in what link is traffic being impacted? Today, there are several ways to monitor these things. I put 3 of them on this slide. At the previous conference, Alexander Klimenko told us about the calculation of TCP retransmits at each link. It's a pretty interesting presentation. There is another solution, mirroring the traffic, which resulted in exceeding the threshold for package buffers. So we can take a package and mirror it into a different interface, and as a result, we'll understand that there is a risk somewhere in the network. And as a result, we can understand what application can suffer or can be jeopardized by this problem. And the third option is traffic mirroring, which resulted in exceeding the buffer and was dropped. So this option shows us that there is a problem. It identifies the problem, and it helps us understand what application is the cause of this traffic loss. So these are the technologies that exist now, that are already being used, but in ITF, there is a working group which is called IP Performance Measurement, or IPPM, and it looks into 2 options of expanded or advanced telemetry. The first option is called a passport mode. In this case, we'll look into the presentation and show you how it works, but actually each transit node adds a portion of metadata to the original package. And then there is additional information added to each package regarding how long each package stood in the queue, and there is also the postcard mode. It's an option where the metadata is not added to the original package. In terms of hardware, it's much easier, but each transit node exports its portion of data to the monitoring station. And I will tell you more about those options on the next slides. Let's look at the INT-IFA technology. It's in those drafts. Those 2 drafts are interconnected. The first line is the first option of this draft, and the second line is the second version of this draft, which are now being discussed. There are some solution components which I put here in a simple way. We have 4 hosts, 2 hosts and 4 transit switches, and this is the traffic flow. Everything is linked to the traffic flow here.
We have Inband flow analyzer domain, which includes all our network devices. The first device downstream is called initiator. Initiator node, the transit nodes are called transit nodes, and the final node is called terminator node. The main idea behind that solution, certainly, there is a monitoring station, a management station, which configures the networks, collects statistics, and does some analysis, data analysis. The main idea behind it is that we are taking the initial package. The first node would add some metadata to that package. The package goes along the network. Every transit node would add its own portion of the metadata, and after that, at the final hop, these metadata would be cut off the initial package, and the initial package would be sent to the terminator node, and the metadata which we have collected on the way would be delivered to the monitoring station for the analysis. The domain boundaries, how they may look like, the simplest way is to include. So it means that our commutators and our routers or leaves will act as initiators and terminators. The Inband flow actually will act as the initiator. And the second option is that when we want to see a more expanded data in the network, we can start with the inflow analyzer on the servers. So in that case, the leaves and spies will act as just transit nodes, adding their own portion of metadata, and the final host will export that to the monitoring stations. So such an option will require some extra work to be done at the terminating stations. How the headers are added in the Inband flow analyzer. The first node would get the initial package, as I have said, and it will add 2 headers. First of all, this is the basic Inband flow analyzer header, which is marked in green, and its own portion of metadata. The first hop added the metadata portion dubbed as M1. So the package goes further. The second host doesn't change the initial header, but would add its own portion of metadata. So it would actually add M2 header. The third host would do the same thing. It would add M3 header, and as far as this is the terminal point, what it does, it cuts off the initial package, the initial data, and would send that to the receiver, and would send the metadata to the observation station. So the metadata may include the identifier of the device, so that we could understand, obviously, every header should be pegged to our network, to some units within the network, so that we can add import and output in order to understand how the flow fared. You can add the information about the outbound queue. You may also add the information about utilization of the outbound port. You may add timestamp of the receipt, when we sent it, when we received it. And therefore, at every hop, we'll understand how long the package stayed within the hop, whether it was stalled by a buffer or not. In terms of the format of the headers, as I said, There are two drafts, version 1 and version 2. According to version 1.0, the header would consist of the basic one, which is marked in green, and the stack with metadata, which would be added by every transit hop or node. In the first version of the draft, it was decided that not to change anything within the IP of the header and to add the event flow analyzer information after the L4 header. And after that, it was decided that probably this is not very reliable. As I said, such a package with additional headers, if it gets out of the network, it would be misinterpreted by the terminating host and will result in some negative outcome. So the second version of the draft implies that a new IP protocol would be added, which says that within the package you may find an event flow analyzer header, and the initial protocol, which now is moved to the event flow analyzer. And there is a stack with metadata available there as well. What options for event flow analyzer are available? So the draft describes three approaches. First of all, here you may find the basic network. This is the original traffic from the initial host to the terminating host. The event flow analyzer may be launched as a standalone probe, which is connected to our commutator, which is being launched, and which from time to time would create some artificial packages with this event flow analyzer header, which moves along the network and which collects the statistics. Naturally, has to be implemented at the hardware level, and the modern hardware allows for that. But as for the probes are artificial, for instance, it may be ping, which is launched between the final or terminating commutators. The pilot and the real traffic can differ. We can create a lot of probes, hoping that they somehow would be distributed along the network, along our hops, and this is how we're going to monitor it. But there is one more option. You may add this event flow analyzer header to the packages sent by the end users. And we are addressing the problem in the sense that we understand that our telemetrics or the test traffic, the users' packages act as the test traffic. And similarly, it looks good, but there is one negative consequence. Don't forget that on the way, the package would get some new portion of the metadata. So on the way, the package would increase in the size. And the possibility arises that if our network on the transit is not fitting the MTU, it means that the MTU package may increase the capacity of the network and will not just lose the monitor package, but we will lose the application package or the user's package, which matters most. Therefore, there is the third option, which is most balanced, in our opinion. This is, again, we have two terminating hosts which are exchanging certain packages. What the first commutator does, it replicates that package, mirrors it, and makes a replica of the package and adds an event flow analyzer to the header. And this package acts as a test one, goes along the network, and goes to the terminating hop, where the telemetric data would be sent to the monitoring station, and the copy of that package would be just skipped. In that case, as far as we are sending a copy of the user's package, we can guarantee that on the way, the routes of the monitoring and the initial package would coincide, and the initial package remains unchanged. So that means that once our network lets through the Inband flow analyzer header, we can be sure that it will not affect the final traffic. It's been supported at the hardware level. So Broadcom Trident 3, Trident 4, Broadcom Tomahawk 4, Broadcom Jericho 2, and Barefoot, Intel, Tafina 2. This all supports that. It should be noted that on that slide again, we find a technical opportunity to implement that this or that matter. What we can do with the devices which do not support INT at the hardware level. So we have a postcard-based telemetry. So its basic description is available from those two drafts. You're invited to start that if you have time and desire. Why postcard-based telemetry emerged? First of all, there was a desire to avoid the harsh requirements to the hardware. Actually, it is a very labor-intensive thing when the metadata are being added to the header at every hop. But still, there are ASICs which have been produced several years ago, and technically they cannot implement that. Besides, postcard-based telemetry can be launched directly from the CPU of the device. So if the CPU is quite old and it cannot add the headers and put timestamps at the hardware level, we still can move the function to the CPU of the device. It would be less accurate measurement, but still it will allow to get some picture as to what is going on. Again, the problem with the MTU, don't forget what we discussed before, the metadata, increase the size of the package, and this is the problem which you have to address somehow. One more thing, postcard-based telemetry allows to send the data out of band. So that means that every node would send its own portion of telemetric data to the monitoring station and can do out of band. So that means that we can rule out the impact of the monitoring traffic to the real queues, which are being used for the final traffic, for the traffic of our applications. How this all works and what regimen are being discussed within drafts. So first of all, this is instruction-based regimen. Again, we have our network to final nodes and the traffic flow between them from left to right. At the first hop in our network, we have to configure a kind of a policy for choosing the packages. It might be a filter, or it might be sampling, when we choose every 1,000th package, 1 in 1,000 package, and we try to monitor the way it goes. After that, we have to identify what data we'd like to export to the monitoring station. And the set of data certainly would depend on the component base our commutator rests on. So it depends on the ASIC and what it can add to that. And an important thing here, the first package would go to the commutator. What happens? This package would be complemented with a header with instructions, and the instructions would define what data have to be exported to the monitoring station. Have a look there, this policy. And the configuration is done at the very first host, at the very first commutator of our network. And naturally, the data would be exported to the monitoring station. After that, the package goes along the network, and every interim node getting a package with a special header, which defines the instructions, which says that certain monitoring data have to be sent to the monitoring station, would read these instructions, realizing what data have to be collected and sent, and finally these data would be sent to the monitoring station. This header acts as a trigger for the subsequent hops and subsequent nodes. It's quite convenient because it is configured only at one hop, and other nodes just follow an instruction, but there is one disadvantage. This initial header added to the first package, and it means that it has to be implemented at the hardware level, which is not available for the obsolete ASICs and obsolete CPUs. There is another regimen called marker-based regimen, the same monitoring station, the traffic flow, but what goes on? At the first commutator, we also configure the policy of selecting the traffic for monitoring. We would configure the data which we would like to export, and at the subsequent nodes, it would be enough just to configure the data sets which we would like to export to the monitoring station. What goes on? We get the initial package, and it only takes to add kind of a marker. Then following that marker, every transit node would understand that once the marker is there. So this is to understand that we have to export the data to the monitoring station. What can be used in case of a marker? You may use flags in the IP header. We can use unused TOS. You can use TEI and CFI bits. The advantage of that method lies in the fact that not necessarily have to add the headers. It may be implemented at any hardware, at any outdated configurator. Only thing you have to bear in mind, you have to agree on how you're going to mark the traffic. But again, it would be enough just to actually configure one bit, which acts as a trigger, saying that this set of data has to be sent to the monitoring station. And the third option, which is the simplest way, which doesn't require anything, any changes in the initial packages. So how it looks like. At all the nodes, we would configure the same policy using the filter for all the nodes. And we'll configure for all the nodes the dataset. And only thing the network does, if this package goes to that filter, the data about that filter would be exported to the monitoring station. The initial package remains unaffected. Nothing is complemented to that. This is the simplest and less demanding in terms of the hardware option. The way you take actually would depend on your requirements and the requests of our customers. Hardware support. I have scratched the surface of that issue already. The marker-based and policy-based options can be very easily implemented at all the hardware types because they do not need any headers to be added, and it should be noted that as far as we don't have to add any new headers to the transit packages, this option of telecard-based telemetry can be moved or installed at the CPU commutator. So it means that we will not somehow monitor the whole traffic, but we'll monitor just selected pieces of flow just in order to have a glimpse of what is going on within the network. And finally, what we have here, let us get back to the flow chart, which I used at the outset. So we have extended the IP performance monitoring to IP performance measurement, and you have two modes or regimen, passport mode and postcard mode. And there are 4 types of telemetrics: in-band flow analyzer, instruction-based, marker-based postcard mode, and policy-based postcard mode.
If this is interesting for you, please look into those drafts, and we will be looking forward to your feedback. You've got my contact details as well as those of my colleagues, and we will be happy to hear your feedback. That's it for me, dear colleagues. I was happy to present this information to you. Thank you, Alexander. I can see that we had 2 questions in the chat, but we've already answered those questions, so we are not going to ask them live. But Alexander, please go to the chat room, and I think there will be people who will be happy to talk to you. And now our next speaker is from NVIDIA, which is an interesting company. It gave us a lot of reasons to send attention to give our attention to it. And this speaker has already been with us at one of the previous conferences, Next Hop. And this speaker will tell us how to put together a switch with an open source. The floor is given to Alexander Petrovsky. Hello, can you hear me? Yes. So that's good. We begin. Hello, dear colleagues. Thank you very much for the introduction. My name is Alexander Petrovsky. I am a staff system engineer at NVIDIA. Before that, this company had a different name, but then NVIDIA bought this other company, and now we are a department within NVIDIA. In this presentation, I would like to tell you about an interesting topic, that is virtual networks. That is their hardware acceleration. That's the functions that are provided by different hardware. So let us start. I would like to start by telling you that today, in today's data centers, almost all network servers are virtual. I'm not only talking about virtual machines or virtual storage. I'm talking about networks. So all network services already work on cloud data centers, on the same servers where we have other calculation applications, and we also add the switches, the routers there. Actually, almost everything that we had before as separate hardware is now used on servers as virtual machines or virtual functions. But in cloud data centers, we need to put together millions of instances of applications, and we need to ensure efficient communication between those applications. The other problem is that those applications are of completely different types. It can be virtual heavy databases, it can be servers, it can be microservices, and it could be many other different applications, but we need to put them together and to connect them. So within our infrastructure, there's often an issue of productivity. And this slide shows an example of what a simplified scheme of a network pipeline looks like, and how we can implement those virtual machines. And actually, anything can be virtual. You can see here that the scheme is quite sophisticated. There are different blocks in this pipeline. For example, here we have a bridge. Then we need to take several more steps here. And finally, it turns out that all those steps are taken by a core on a central processor. But the central processor is not designed very well for processing network traffic. And this is a problem of productivity, particularly if we try to use virtual servers on a central processor at the core level. So here's an example of where we have the bottlenecks in terms of productivity. I will show you a standard scheme of a virtual switch. This is how this simplified scheme looks like. There are virtual machines which are connected to the host thanks to different interfaces which are added to Linux bridge, and then it all is routed via the OVS bridge. And there are 2 points which reduce the productivity dramatically. The interface itself between different virtual machines. For example, today there are different interfaces in Linux which are used for connection between the virtual machine and the host. So it's all in software, there is no hardware, but this process is very inefficient. The second point where we'll lose our efficiency is the per-packet processing in software, which is very inefficient. This is because it treats package by software, which is very slow and inefficient, particularly when we have a lot of small packages and a lot of different paths which need to be put together. And according to our latest tests, if we have a powerful server, we will only have about 500,000 packages per second, which is very little. A normal modern application can't work in these conditions. So what are the approaches? What are the ways out? The first approach is quite obvious. That is, trying to optimize the processing of the CPU packets. We can implement fast path on the CPU. And there are 2 main approaches here which are very popular today. The first one is called Data Plane Development Kit, DPDK. We use bypass here. We use the drivers and the network cards, and they are all moved to the user space. As a result, we jump over this kernel, we bypass it. So all the kernels are used purely for data processing. And we move the additional operations to the user space. And as a result, we can send some packets directly to the user space, and it's pretty quick. So this technology is quite popular. It's used in many places, and according to our latest tests, for one kernel, we can have pretty good results. If we have more kernels, let's say 12 cores, then we will have more than 100 gigabytes. This number seems to be pretty attractive. There is another technology which is being developed in parallel. It's called XDP, Express Data Path. And it's based on another technology which is called peer-to-peer. Unlike the DPDK technology, it's a fast bus technology. We have in-kernel packet processing with user-loadable eBPF program. We put this in the kernel, and it's done in a protected sandbox in the kernel. This is a pretty fast technology which also uses DMA in order to get the packets from the hardware and put it in the core. And XDP is a solution which includes eBPF. As a result, we can have very effective network operations at the kernel level. And we can start data processing. This technology is pretty popular. Linux is developing it rapidly, and more and more people start using this technology. In terms of performance, it's a little bit slower than DPDK, but it's keeping its pace, it's advancing on DPDK, and it's becoming more effective. So this is the idea. How can we do the virtual switch faster? We can use DPDK, rewrite it, bypass the kernel to increase message rate, and this is what we get with OVS. With the ordinary bridging, we have a 12 megabyte kernel per core. So we resolved some of the problems, but our interface is still having a problem. It's still pretty slow, but we got another challenge here. We have the VM interface, which is still virtual. It's software. And there's another issue. I already showed on the previous slide that we can get almost 80 BPS per one kernel. But as soon as we add complexity with routing and bridging and package filtering or firewalling and so on and so forth, our productivity drops dramatically. So this solution is not scalable at all. And this is where we can have the NIC hardware offloads technology. How did those network adapters develop historically? About 5 years ago, only basic technologies were provided for stateless offloads, for example. This is the checksum. Then there is the LSO technology to connect different packets or packages, and there is also the balancing technology and so on and so forth. But advanced adapters support more advanced offloads, and they can take on more functions. I'm talking about the SRIOV technology, the VertIO acceleration technology, and the hardware steering and switching technology. There's a number of other things which can be done by network cards, that is Qrator, some security technologies. Unfortunately, I don't have the time to tell you about that, so now I'm going to focus on some network offloads, which resolve the issues of virtual networks. So how did we develop the processing of network adapters, network I/O? This is what we are moving to. As I said, we start with a regular network card. Here we have networking, or it's somewhere in the core or in the user space, and we used to fully process data and control plane on CPU. Today's cards are called control planes on CPU. Actually, it's smart cards, and this is the idea. We can actually move all those processes to hardware. And this year, There is also the notion of DPU. It's also an adapter which can have more functions. It can take on the full I/O, which becomes flexible. So this is where existing network adapters evolution to. Let's now talk about the SRIOV technology, which provides native hardware access at the virtual machine level. Every virtual machine has direct access to the network adapter, but this virtual machine thinks that a driver is needed for that adapter, and there are also some other issues. So this is not a very flexible technology. And there is another technology which is called VirtIO. This is a standard virtual interface. This is purely software. The performance is pretty slow, but the interface is flexible. It doesn't require any drivers within the virtual machines, and it supports all the classical functions such as virtual migration and so on and so forth. But it can also be connected to other technologies that I will tell you about later. There are two other concepts which are used for network acceleration. The first one is called VF representer. SRIOV is a pretty old technology, but we can use the PCI and the network adapter, and then we connect it all, but we lost the possibility to control those virtual functions. And in order to deal with that issue, we introduced the VF representer port. The idea is that we have a virtual device which represents each of those parts, and it's called a representer because this is what it does. It represents virtual functions, and there is a control interface there, which can be used to set up those representers. For example, by using the representer, you can change the settings of the queues and so on. So the port representer is a standard interface, and you can do anything with it. You can send traffic to those representers, but mostly they are used in order to set up the virtual interfaces in virtual machines that you need. The second important part is the so-called embedded switch, or E-switch. This is a special block within the network adapter, which ensures the flow-based packet processing. In essence, it's a flow-based switch, which has several different tables which are interconnected, and each table has a lot of match-in-action records. It can use headlines from the Ethernet packet, and these packets can be sent to another route. You can change their headlines and so on. So this is what you can do within the E-switch, within the network switch. If we put all those technologies together, we can have a technology like this. We have an HV data bus, or E-switch, and this is where we send all this data. And this E-switch looks like a table where match is connected with action. And there are also 3 virtual machines here, and the traffic is sent via those machines, and the adapter sends the data between the virtual machines and real hardware, and it's controlled in the host by the port representer. This technology also works with SRIOV and with VirtIO, where we do a certain relay of the interface by means of a special backend application. And as a result, we have a virtual function, and the virtual machine doesn't even know that it does not deal with virtual functions. So talking about DPUs, these are devices which do data plane, but also control plane. Then the solution is even easier. It's even more simple because we have data plane here, we still have the E-switch. The complete scheme is the same, but we control everything within the DPU adapter, including control plane, including SW data paths, and so on. The host only has an interface which is sent to the virtual machine. The advantages are that we reduce the work of CPUs, and everything is done by DPU, and we isolate the host, and the DPU can undertake some network functions.
And any I/O functions as management or storage or security. So this is something attached to the standard CPU. This approach can be implemented the following way. Two ways, actually. The first option is by means of Switchdev. This is a standard data plane option for Linux kernel, and it looks the following way. There is an integration with Switchdev, and VS would use a special IP in order to offload its flows into the switch card. So the Linux traffic control would be used for that. This is a standard Linux service, and as soon as OVS has formed the table, it would be downloaded into the network card chip. So you may offload the whole data path, or you can do that partially. This is an example of how you can configure the data flow by means of Linux TC manually. This same approach can be used for DPDK. As an example, this is OVS DPDK. So this is called generic flow API in DPDK. So it builds the table by means of RT flow. It would be downloaded to the RT switch. The same functionality. Support of offloader. But the only difference is that it is being used for DPDK. So this is an example of how the flow can be created to ingress pattern. I already said that such two approaches are totally hardware-based, and they can be brought together to make a compromise solution, which can be accelerated. You would use the VDPA approach in order to accelerate the RTO network. You have two machines, but you would get a special VDPA control and block. It may be implemented as a DPDK application, or, for instance, for kernel 5.0 now, it's been added to the upstream kernel. So this is a special control which brings the virtual adapter and Virtio in order to map the memory for Virtio into the hardware. We would get the same preferences and privileges, but at the same time would get the zero load of the Virtio at the CPU by means of offload. And we will not modernize customer awareness and would get the live migration support and now guest awareness, but at the same time you have to balance between hardware performance and software flexibility. So this is somewhere between the purely software solution and hardware solution. So the last record which we hit would be 20 Mbps. So it means the data path I/O can process as much data as that per second. And there is a big list of offloads that when network adapters can do, starting from lag bond ECMP You can do that for any kinds of tunnels and overlay networks. There is a support of different COS functions, and there is a support of the security functions, for instance. L4 firewall and stateful L4. So it means that the whole network stack can be offloaded onto the DPU, and the CPU will work purely for the computer. A couple of words about the solutions which can use this approach for. Today, the main focus in the development of different offloads would be OpenVSwitch. This is an open source project with a big community. We are also part of that community. And this is the main focus in order to add more offloads there. There are two options of the OVS. OVS kernel is a kernel module, or VDBK module when part of that functionality is performed as DPDK application. There are lots of open source OVS-based solutions. This is about OVN. The OVS control. OVS is a part of the OpenStack Neutron, and since recently, Kubernetes such as OpenShift CNIS will be used along with the OVN, or there is a new project which is called Antria. In essence, this is the SDN for containers. The same solution is being used for some commercial projects, Nokia Nuage VCS, and quite recently a Monterey project was announced, which includes the NSX acceleration. Let me tell you about a very interesting case which acts as at the concept level, exists at the concept level, and we have that by the end of the year it would become a ready-made project. The idea behind that is that we're using the same approach, but in telco, the network function can implement its own network functions within itself. So some virtual machines would do the load balancer, another VM would act as a gateway, and another one would act as a switching. They would need compartmentalization or isolation between them. It can be addressed by the following. vSwitch and eSwitch would be virtualized, meaning that we'll create several virtual cards tables with eSwitch embedded eSwitch, which will act simultaneously in parallel. So the control plane VNF would be located at one virtual machine, and the whole traffic would go through the virtual NIC without going to the CPU, and it works at the speed rate of interface. This is a solution how the offloaders can be used for 5G telecom. Let's look into the future, what we have to await in terms of acceleration. First of all, we run into the situation when CRV has become an outdated one, quite old one, and it has its own limitations. The biggest limitation is the number of virtual functions which can be created by the operator. At the moment, these functions are numbered in hundreds, and it actually does not support VF. And a PCIS function is being developed for that purpose, so it's kind of a lightweight CRV. You can use this CRM function in order to create a comprehensive solution to accelerate the network, the virtual machines, containers, and even bimetal servers. The device would be divided into smaller devices with sub-functions, so these are not the full-fledged servers, but they would have their own policies, their own ports, and in Linux, sub-function would be called a mediated device, a separate device which can be moved to the container or to the virtual environment, and it can be used in order to transmit the data. And you can actually replicate that and scale it up means that they can be turned on and off. So the subfunction, this is the future of scalability of CRV. The second thing where the industry is heading to, this is about unification. Unification of infrastructure for host network and storage security and management. For bare metal server, unified infrastructure is going to be set up for networking, storage, security, and management. Any I/O can be accelerated for any kind of load. If you compare that to what is available now when Hypervisor acts as a unified platform, which would contain some virtual functions of network I/O, storage I/O, security, and crypto I/O, and host management. And all the containers and virtual machines would be operational on that basis. So this solution is available there. It's quite flexible, but it is slow and non-efficient. Why this all has to be transformed? Because the I/O will go to the DPU, a separate device, which will implement a network, storage, security, crypto, and management functions. It would isolate that from the host and from the virtual machines and containers. In the virtual case, we'll have a lightweight hypervisor, which will do only the CPU scheduling. This solution can be used along with the hypervisor and bare metal servers, which until recently could not adapt for that. In that sense, we are unifying bare metal infrastructure and the virtual infrastructure and the container infrastructure to accommodate one common functionality, which is implemented at one CPU or data processing unit. That solution has been recently announced, so for some time it's been implemented by different cloud companies. And now it goes to the enterprise solution. Quite recently it was announced by a company dubbing that Monterey project. So stay tuned, follow the news. I think that in the upcoming months we'll see a lot of solutions based on that concept. Colleagues, this concludes my remarks. Thank you so much for your attention. If we have time for questions, I will gladly take them. I think it was a very hardcore talk, and we're going to break, but we have a couple of minutes for Q&A. First question was from Michael. How do you provide for Michael migration? Actually, if VS is not participating in I/O. In live migration, in the live migration of the virtual machines to another host, for instance, at that host, there might be probably some fast pass which is being implemented within the network adapter. It will not take the shape, but Virtaio advantage lies in the fact that once we don't have needed flows within the fast pass, the package, which goes to the adapter, and the adapter fails to find the appropriate policy. In order to process that, it will go to CPU. And therefore, the migration of the virtual machines would work natively without changing the concept itself. When the virtual machine goes to the destination machine to another host, the packages, for some time, the first passages actually would go to the CPU, then offload would take place, and other packages would be offloaded and go through the network adapters. Thank you so much. And the second question is from Evgeny. At early network adapters, there were balancing problems. All the packages would go to the zero kernel and would not be balanced between the CPU kernels. Is this problem addressed? Well, yes, this problem has been addressed long before. The IRS technology supports the ability to get the package hash from any part of the header. And within our adapters, we are supporting any kinds of tunnels. And the network adapter can look into the inner header and take hash from there, and therefore balance the kernels efficiently. Thank you so much. Okay, so this concludes our session, and we break until 1 p.m. Thank you. We are back, and our next speaker is the guy who we invited for 2 years, but unfortunately he could not show up because he was tuning the most sustainable IPX for our users. For him not to be bored today, we invited him, Boris Lytochkin, who will tell us about how to build an OpenVPN server for big clients. Hi everyone! As you know, from geography, sadly, if you have not forgotten that, we have 5 oceans on planet Earth, but last year one rat last year made us discover the 6th ocean, the ocean of the remote or distance work. And all the companies embarked on building the fleet in order to charter these waters. In the upcoming 20 minutes, we'll look at the fleet of Yandex, which helped us to cross this ocean of remote and distance work. What usually is implied by OpenVPN? Usually, this is a kind of a hardware or some solutions by VPN manufacturers. If this is your case, then in spring you gladly accepted the help from your provider who helped you the VPN support to survive through the pandemic. So the lockdown is not over, although this is autumn already. The temporary licenses are no longer valid, but how you can do without licenses and extra costs? What if you use open source in order to get a good solution, a good fleet to charter through that ocean of work from home? In order to understand what a good fleet is about, let us define the criteria. For me, I have defined 6 criteria which the building blocks and the fleet for our scenarios should meet. First of all, no special hardware requirements. Regular servers are needed, just ordinary servers which are available from any rank-and-file shop. It should be open source. In order to kill 2 birds with 1 stone, first of all, you don't have to pay for licenses, and which is equally important, you can take original codes, and once you detect certain problems, you can remedy that on your own. And the solution which you need, sadly, should be applicable to all widespread OS, and Yandex, for instance, uses 5 of such OS. This VPN should run on UDP or TCP/IP2, these protocols. That's very simple. These are the 2 protocols which are most appropriate or infrastructurally more adequate in order to get through the firewalls which you may find in the airports or hotels. And it should be high-load solution, it should be robust and fault-tolerant or fault-resistant. And the last but not least, probably even the most important one, it had to be rocket-fast scalable in a linear fashion. Stop, why was I speaking about OpenVPN by any means? Let's discuss that on chat. Now, you have the voting device. Tell me, how many of these points of 6 criteria would be met by OpenVPN and the OpenVPN-based solutions? And while you are taking these questions, let me tell you about myself. I'm working for 12 years in the telecom. I'm building data centers for Yandex, and I'm working for the market warehouses, so I'm present in almost all the networks of Yandex. I've left my footprints everywhere. Back in the university, I did not study the mathematical analysis, but dived into the computer science instead. I've spent a weekend to restructure our VPN so that the whole company could switch to the work from home mode. But nothing awful happened ever since. We didn't have any complaint about the problems with VPN which would deal with the infrastructure of the system. I think that we have all voted. It's high time for us to find out the appropriate answer. And sadly, all the 6 criteria out of 6 have to be met by the OpenVPN. Let us look in more detail how it can be done. Most importantly, OpenVPN, this is a process which works as a single thread server. So it means that at one moment of time, the OpenVPN can do only one action: to encrypt or decrypt the packages or identify the clients. And while it is doing one function only, other types of functions are lining up in the queue. Our main objective, our main target there is to make sure that OpenVPN spends as much time as possible on the processing of the packages. And we have to configure the OpenVPN the right way, make it right. First of all, make sure that your whole fleet, both the servers, the clients, this is very important, should work on OpenVPN 2.4 version. Why? Because they have the crypto which act as the counters. Without deep diving into the mathematical details, actually, you speed up your rate almost 2 times. And in TCM, actually, on mode, the OpenVPN would act 2 times faster. Sadly, it works in UDP. If you open OpenVPN website, there will be a very interesting article which in several paragraphs describes that.
And now we'll talk more about the server part, because clients as such are not of such a great interest to us now. Please make sure that you have IaaS Crypto Accelerator on your server, AESNI. Enable the VPN so that it works better with the socket. And furthermore, make sure that OpenVPN is fine-tuned for the processors, for the network cards, and all other features that you can find in any documents on high-load networks. And now about authentication. If you use certificates during authentication, and you should use certificates, so when you check them, please use the additional function of DIR. And furthermore, you need to ensure a basic DOS protection. For every VPN, you should have 1 certificate per device. There should be an individual certificate with its own individual serial number. In this case, if a device is compromised, you can ensure an employee's access via other devices. Furthermore, you will also be protected from DOS. You just use the OpenVPN patch that is available on this link, and then you can use this patch. Actually, it's located in the upstream of OpenVPN, but if you want it to be in the 2.5 version, you can ask the developers to do this. And now, regarding authentication, what solutions do we normally choose? Of course, it's all about scripts. Client connect, client disconnect, those are all our favorite things. Can we use them when the load is high? Obviously, no. Why not? The reason is the same. While the script is working, OpenVPN waits for packets to be piled in buffers, and then the clients will see losses or delays. So what are the alternatives? There are 2 of them. The first one is to use management socket of the VPN. As a result, there will be a sidecar daemon talking to it, and there will be information on authentication exchanged. As a result, overhead expenses will go down. Furthermore, there is recently a plugin subsystem which can be connected with a dynamic library, and the OpenVPN will talk to a certain method in a specific situation. I found two examples of how this plugin can be used in these situations. The first one is a two-factor identification, but it only uses one method in the plugins. And the second solution is much more interesting, and it's done by a Russian developer. You use an embedded Python interpreter for all plugin methods. You can do this right on Python, and we really liked this idea, and we decided to use it in our environment and to fine-tune it a little bit. This is how we launched the Yandex plugin VPN. It also has a Python interpreter, which is initialized upon OpenVPN startup and keeps running, saving its context. It's all about the code, and it can speed up the things. If you don't need a certain method, you just don't include the relevant code, and the plugin will not include it in its work, and OpenVPN will not waste time. The typical plugin call uses the fork and give control back, and it takes less than 1 millisecond. Well, it's easier to see it, so we published it on open source. So please visit our GitHub, and you can use this plugin. I hope you will like it. So this is what regards our OpenVPN process settings. But what about the scalability or the possibilities for this system to grow? As a rule, the speed with which the OpenVPN processes packets is not an issue. The bandwidth is not an issue. You can see that sometimes it works with 900 megabytes per second. I don't really believe that, but anyway, 200 megabytes are okay. But there's another issue. That's the time you need to spend on service data processing. And here is an interesting example. Let's suppose that the typical session of an OpenVPN client lasts 1 hour. What will happen during this 1 hour? There will be one authentication, one authorization, 4 re-authentication, TLS key refresh, and 1 disconnect. 7 events where we need our plugin. Let's suppose that we wrote it badly in Python, or maybe we address a remote server very far away. And let's suppose that every plugin call will take 20 milliseconds. What does it mean? As a result, the jitter for the clients will grow, delay will grow. And I really like the option where we have 60 connections, and there is the mean jitter of 2.4 milliseconds. That's the maximum that we could afford. We can't go any further. But if we have 7 plugin calls of 20 milliseconds and 60 connections per process, how do we ensure the connection of 20,000 employees? That's easy. We need to have more than 300 processes in OpenVPN. And for that, we need to load balance. Let's talk about load balancing. We can do this balancing incorrectly. For example, we can put all the 300 records of our servers in the DNS. It won't work. Not many clients are able to work with such a huge number of records in principle. But there is also a pretty unpleasant type of clients who are going to modify those records and change their order and so on. And we can also use an external load balancer. It's quite clear. There is good software and hardware, but this is yet another point of failure, and sometimes it requires additional hardware. Along with the load balancer, we can use Anycast. Anycast can't be used for OpenVPN for the same reason why we struggled with Jitter. That's because this is another rerouting of your network, and as a result, the traffic can go to another server as a result. So how do we balance those pools correctly? We probably need to use our load balancer right on the server, per server LB. And we also need to use our clients directly by switching on the remote random option. This is a pseudo-random function, and as a result, the information will be distributed pretty equally between the servers. How do we use this local server load balancing? We can use a system which is called IPVS. That's for Linux. It's a pretty good system. And we can add some health checks to it. We can use some sockets that work with OpenVPN, or we can use the process so reuse port, which is used for the same socket. And there's another option, FreeBSD or setSockOpt. So let's try drawing a little bit. Here let's have 4 processes or OpenVPNs that use the same UDP port. To balance the loading in the core, a very simple hash function is used in this core, which distributes the input traffic based on the headers of the packets. The reverse traffic is not hashed, of course. And it may happen so that we have a failure in some process, or we can add another process, and then the hash function will change, and the packets that used to go to process 2 will go to process 3, and the clients will be disconnected. It's not very convenient. This is not what we wanted to have, which is why we prepared a small modification for this function. In addition to the hash function, we drew a table with the sessions, and this is important. When there is the first outgoing packet from the client, when the client sends you the packet, there is a record in the table, in the status table, and the following packets will be sent to the second process. And it's not based on the hash function, it's based on the state table. Of course, this patch is available in the open source. You can use this link and join our discussion there. But let's see what the client's configuration looks like if we use all those practices. This is what it seems to be like. In config VPN, we have a certain number of servers, and there is also the remote random option. And we also use DNS, and we write IP addresses for each record. And it would seem strange to talk about all those little things that we did to connect all our employees without mentioning what we really had in practice. Let's look at March. That's when our company started working offline 100%. These are the traffics from the users, and that's the weekend where I had to reset all the groups of our servers. So from Tuesday till Thursday, we had a triple capacity of our virtual servers. And this is what it looks like now. This is a geo-distributed cluster. The servers are located in different locations. If there is a failure, no one will notice anything. There are 20,000 simultaneous connections. There's more than 20 gigabits per second throughput. It's scaled threefold within 5 days, and we can keep scaling it without any limits. We just need to add servers sometimes. So what happened at that weekend where everyone went online? Let's remember those sockets. We had 4 processes on those sockets. Everything I had to do to make 21,000 connections instead of 7,000 connections, I just added some more processes. And they used the same patches in order to build themselves into that group. So it was quite easy. When we did all those changes, it was obvious that we could simplify the client's work. Adding one server means that we need to amend all the configurations on all other servers, and it's very inconvenient when we talk about thousands of clients. So we added another patch which implements a standard mechanism. That patch is available. It was made available by OpenVPN developers, so you can look at it. We will be happy to get more feedback. So that's it. To conclude, I would like to thank my colleagues, without which 2/3 of my presentation would be impossible. I thank Mikhail Orekhov, Artem Rudenko, Andrei Lytochkin, Vlad Grishenko. Thank you very much. I would not do this without you. Well, was I able to convince you that OpenVPN can ensure all those 6 things? Please answer this question. As Andrei is getting the most interesting questions from the chat, I'm ready to answer those questions. Thank you. Thank you, Boris. Well, you can actually make a trolley bus out of bread, but why? You already have everything needed. So if you haven't asked your questions yet, it's high time to do that. And the first question to Boris: how many people ensure the work of OpenVPN at Yandex? Answer: well, we have 7 persons on our team right now, and each of them is involved in organizing those servers. But along with OpenVPNs, we also support all corporate networks, including those that work with the warehouses and markets. Thank you very much. There's another question. Well, we are looking at the alternatives of WarGuard. WarGuard is not a bad option, but WarGuard does not implement some of the functions we need. For example, it doesn't work on top of TCP. And for a big company where people have a lot of business trips or used to have lots of business trips, it's a very important feature to get connected to the VPN. But we are looking at Vanguard. We hope they will do this. So we wish them all the best. Let's wait for your presentation next year, right? Yes, let's hope for it. And there's another question from Vasily. Can we flood the custom connection table? Yes, we can flood it, but the OpenVPN is only responsible for clients who did authentication. You remember that I mentioned the disconnection of the VPN set option. So if you haven't provided your private key, the OpenVPN will not even answer. It will not even respond, so there will be no change in the status table. There is another question. All those Python plugins, are they really better than the standard methods? I didn't really understand your question because the Python plugins are actually needed to process all the fields correctly, and we need to ensure the split tunnel and the necessary radius. All right. A question from Megabytes. Mikhail, 5 megabytes, do you think it's not the best productivity? Well, it's enough for us. Fair enough. Well, let's wait for another minute. Maybe there is someone else who would like to ask their question. Let's wait for half a minute. Well, let's look at the results of our poll. Well, look at this distribution. 41% of respondents believe that VPN is capable of all 6 functions, and the others decided to mock at me a little bit, because the OpenVPN, as they said, is only able to process 3 functions out of 6. But this distribution is great. Let's look at answer 2. 55% of the respondents said that OpenVPN is now held in high esteem by them, and that they are ready to install OpenVPN right now.
One more question. Why stateful tablets? Why not stateless? Resembling, well, stateless implies hash functions, and if we change the number of servers or processors which are servicing such a load, then the hash function would change, and the hash value would change, and the client's session would just get out and go down. Okay, thank you so much, Boris. Thank you for your presentation. Join our chat. I do think that people will have more questions. You are invited to ask them on chat. Boris, thank you. Thank you. Bye. See you. Next pitch would be made by another company, another hyperscaler for the Russian environment. It's a pleasure for us that this company received our invitation and joined us for today to speak about our domestic kitchen. That will be mail.ru. Alexander Pavlov, who works as deputy director for the operation of the network, he will tell us how to actually get protected against ruffians and how to protect against DDoS. Actually, it will be my next presentation. DDoS, and I hope that you can hear me. We were some technical glitches, this kind of a TV breach. Yandex to mail.ru. My name is Alexander Pavlov. I'm from mail.ru. It's quite rare occasion that we're speaking at conferences. I'd like to make a U-turn there, and the very first presentation is ripe and mature. When I got prepared for that presentation, I wanted to change the topic. How to make a Linux-based presentation, and is it possible to? But as far as this is the topic which was announced, I will tell you about the DDoS fight. First, I'd like to tell you about the mail.ru network. It does exist. It's quite big, quite vast. Actually, the consolidated network gives more than 6 terabyte BPS, and we have native traffic. We have a free band, and we thought about how we can use that. And first, what occurred to us is to get dirty traffic, to purify it, and not to use the outsource services of other companies, trying to do that in-house. The second idea was a crazy one, to distribute home internet, but I think that we are late about that, and someone has invented that already. I'm actually love very much Hinderside, and probably I'm old enough. It was 2016, I was young then, and the network of the company did not run into any DDoS problems. Either DDoS attacks were minor ones and could be protected at level of the server, or if they were huge, then SuperNox would be engaged, that heroically would generate filtration policies and would generate firewalls which would bash aside the DDoS attacks. And we felt being heroes, and this was the problem, as it turned out. Before deep diving into the problems, let me show to you the statistics. Kaspersky Lab discloses that every now and then, and it showed that the length of the attack increases year on year, so meaning that the short-term attacks now account for the overwhelming majority, and TCP and Synfloat attacks account for the majority of the attacks. We realized that we have to change something. Once we saw the increase in the number of attacks when their sophistication increased, and SuperNoc could not cope with the rolling out of the policies and rules. We are SuperNoc, but still, due to the limitation of our resources and the resources of the equipment and the reaction speed, we could not catch up with the DDoS. Actually, we spent about 20 minutes to bash out the attack, but the attack itself did not last as long as that. You could roll out a firewall, but by the time you install a firewall, actually, the DDoS attack was lower. Router filtration was not enough, as I showed to you. You cannot somehow reject or repel such attacks at the server level. And we launched a very good product from Cloud Solutions with the outsourced projects and outsourced clients which would like to protect as well. First thing we did, sadly, we used a NetFlow collector in order to understand what is going on. We had certain requirements in the sense that there should be a clear-cut API in order to give us not only the treated but also unpurified data to analyze. We had to automate all these things to connect them so that it gets connected with our internal systems and provide us with the necessary analytics. We looked for paid solutions, MyEngine, something like that. And we ended up with the NFSen. This is a two-component solution. And the collector, which connects the data. And it could be inquired. And as a network company, we are fond of Python. Unfortunately, this solution is a statical one. We selected the thresholders, which described our resources in terms of the traffic and the deviations from the norm, and we wrote on the chart. And the more detailed information would be provided via mail. The reaction time amounted to about 2 minutes due to the fact that NFSen has certain limitations and restrictions, and it is also complemented by the analytics. This is a case of a report. And certain hosts are being attacked using EDP protocol. And these are EDP fragments. And remember, I'll show to you the statistics that most of attacks are SYN ones, and until now we do not know how to reject them. This is a problem which we had to address then. We tried to address that by means of internet. We surfed the web and we found a SYN-Cookit solution from Biget company. This is a hosting operator which run into the same problems as we do. And they designed a SYN-Cookit solution which protects the system from SYN flood and ACK attack. So you get a SYN package. You embed a kind of a cookie and you send that to a host, and it should answer with ACK using the same cookie. So it means that you reject the SYN attack 100%. It worked quite fast. We actually tuned a little bit so that it works from a cluster as well, so that's good, but there are some nuances. Just like any DDoS solutions, they are far from being perfect. This is about customized kernel. In order to, once actually you realize that you have a validated package, and it includes a kind of a cookie, you have to customize your kernel, and it was not appropriate. It was appropriate only for Linux. Non-Linux machines and the third-party projects, which for security reasons cannot install a customized kernel, they could not use this solution in order to reject DDoS attacks. Actually, we addressed part of our problems by means of that solution, but another part remains. It takes far too long, actually, to detect an attack. And if it takes a little bit more than 2 minutes, then we believe that this is too slow. And we use configuration of the network when using SYN-Cookit solution, again taking time, and we wanted to protect the third-party projects. So the slow mitigation problem was addressed the following way. We also surfed the web, expecting that we would find an appropriate solution, but unfortunately there was nothing appropriate, nothing which would meet our requirements. We needed fast mitigation, integration with our resources, systems, and we wanted AP, but we failed to find that. Just like any people who can write a code and who run into these problems, we decided to write our own program, our own software. We used an open source components aggregated with our own code. There is a scheme of our solution. I'd like to say explicitly that it is totally redundant. It is located in the cube. It is ready for the failure of a data center. It may migrate very easily, so the redundancy is quite good, and it consists of the following items. BGP, which gets all the BGP routes and BGP data from the servers, from all the border routers, and the routes would be aggregated for the statistics purposes, and all other units actually are connected to the system. There is a Go flow, which receives net flow, bearing in mind that the borders are different. We have some servers which receive the net flow as well, and means that we need different formats. This actually would be driven to Kafka, NOC Kafka, and IP addresses would also be collected. And this has been stored by NOC Kafka, ready for analysis, and it would be used by multiple systems of our network. 3 of them have been listed here. I will focus on DDoS mitigation system, which we designed ourselves. And actually, we wrote that using Python. regardless of the servers which are sending some flows to us, so we actually have 10,000 of samplings, and number of routers amounts to 32, and we had about 120,000 flows. We tried to sparse that, to analyze that, to take certain decisions. And it means that with intervals of about 15 seconds, we collect the flows and we analyze that. It takes about 1.5 minutes using Python, and probably we could optimize the code, and probably we could even dedicate some CPU memory. But our target is about 15 seconds, that we have to squeeze within these 15 seconds intervals in terms of analytics and collection so that it works smoothly. And it was a far cry from these 15 seconds, and we thought that probably Python was not appropriate to attain this goal, as far as we had some expertise in terms of Golang. Actually, we rewritten the code in Golang, and we were surprised at the speed. So it was clear that it would be faster, but not as much, actually. The analysis of the data is 7 seconds only, and we actually reduced the CPU utilization and the memory use utilization. On that slide, you can see all the metrics which we are collecting. I will not deep dive into each of them. I hope that the presentation would be uploaded. And if you're ready to discuss, I will be glad to join that discussion. These are the metrics which we're using for the analytics purposes. All the data actually would be stored in the ClickHouse. And just like any technical presentation, we could not do without flowcharts from Graphon. Handy to understand what is going on with the system. And the next problem, which we touched upon, this is about the manual configuration of the border in order to purify the traffic. A man is lazy by nature, and we try to automate all the things possible so that people work less and are happier, because the happy operators will not leave the company. How we address this problem? I do think that flow spec is quite familiar to everyone, but usually this would be used in its textbook meaning, so that the traffic does not overload the uplink. You delegate the functions to the uplink and billing, but we moved a different way. As I said, we have a free band, and therefore the flow spec actually was launched our flow spec. We actually made kind of a binder, and it looks the following way. It contains an IP. The administrator may automate the system on his own in order to do some filtration of the project. The old school operators may do that on site, so it's quite easy, quite understandable. It should be noted that as an administrator, you may choose only your own resource. So that means that the administrator goes there. All the data would be validated and sent to the network for redirection. So either we would drop or redirect. So we do not know how to use the IP action. So we use drop redirects in proxy, and I will tell you about the next redirection a bit later. Next problem which we run into is that it is not appropriate for the third-party projects or for the hosted projects. All the solutions which do exist there are not appropriate for that. We serve the web, and we were told that there is a gatekeeper solution. According to the designers, to the developers, It is horizontally scalable. It allows for dropping, redirection, and even the developers themselves are happy with that. And probably this is why there is now public release of that product. We released beta versions with lots of bugs. We exchanged letters with the developers, and once we launched that, it turned out that it's quite good in terms of capacity. And you can use dynamic rules for filtration, so it means that our DDoS mitigator may show how much traffic we receive, and you may change the policy. You may add certain rules to the filtration, and would be immediately applied. There are some shifts and other features. And by the way, we actually broke the VDP filtration of the gamers. We know actually how to tell the valid from non-valid traffic. And we can actually somehow mark that in order to understand whether this is our traffic or not our traffic. There are disadvantages pertinent to that, like for any DOS solution, meaning that, first of all, rate limiter is based on the DPDK, and this rail limiter actually can be used when you drop the right packages, and so this is what we can address by means of generation of right policies and data analysis. And until now, this solution cannot work with the network cards with a capacity of more than 10 gigabit. The developers promised to address that problem once they release the product. So this is how the gatekeeper scheme looks like. It's very simple. It consists of two components. First of all, this is the gatekeeper servers installed on the border of the network. With billing and uplink, where we have to purify the traffic. The hyper servers actually would be installed, which can be scalable horizontally. It means that you can install lots of them, and they would be limited only by the routing port. So the second part is the grantor server. This is a kind of a shadow cardinal, which takes all the filtration decisions and which would upload that to the hyper servers.
On the whole, we have tested this solution. It's pretty fast. And we are planning to organize a pretty large setup of this solution. So what comes next? We'd like to move on to a better interface. For example, 100 megabyte. And right now we are also launching a web portal to counter attacks. And we will show all the statistics and the analysis to the administrator. We will provide the picture as to how much of the traffic was useful and how much was dirty. So that's all what we have with respect to fighting DDoS. Thank you very much. This was Alexander Pavlov. Thank you very much. We have several questions in the chat, so don't hesitate to ask more questions. There have been two questions which I will put together. Is there support for mail.ru service, and what are the protection measures at IPv6? Well, as for IPv6, at some mail.ru projects, we have this protection. We considered IPv6 at the stage of solution analysis, and actually our solutions are good enough for IPv6. It's suitable. Right now, the part of this traffic is not very big, so we don't have these issues, but the solutions that you mentioned are okay for IPv6. That's good. And now there's the next question. Why there is no ITP in your solutions? Well, that's a good question. I probably was unable to put this into my presentation, but of course, we do use this solution. We analyze all the attacks. There were many attacks like this 2 years ago, but now there are not so many such attacks in our network. So maybe this is why I didn't include those solutions in my slides, but of course we do collect metrics for these types of attacks. There are 3 more questions. Well, in Linux, there is a cookies prism. Why didn't you like it? Well, once again, we wanted to introduce a general solution. SimCook. It's a new version of this solution, and it can work within a cluster. But we wanted to have some common platform which we would use to protect ourselves in order to make sure that this system is more flexible. We didn't want to set up SimCook on each of our resources. There are also front ends where we terminate our traffic, and in theory, we can protect a non-Linux resource. We only did this with our projects, not other people's projects, because they can't give us their certificates. And this is a continuation of the SimCook solution. It's a cluster platform, which is pretty big, and we have heterogeneous projects, and we can protect all of them with this solution. All right, that's clear. And the next part of this question is as follows. At what points do you collect the traffic? Actually, we do use borders and aggregators. Our aggregators have the same setup. And within this presentation, we had to look at borders. Of course, it's assembled on borders. And we would like to have a net flow that would be good for security features. But of course, I haven't seen any network equipment that would be capable of transferring net flow one-to-one. We really want this solution, but we prepared another solution that I would probably share with you in the next presentations. While talking about one-on-one solutions, maybe you need to do this online. Yes, it's not very scalable. And there is a question from Nikolai. What's the speed of attack mitigation? Yes, I think I skipped this in my presentation. It turns out that we aggregate data for 15 seconds, and there's another 7 seconds. That's a maximum. So that depends on when the attack started. If it started at the beginning of those 15 seconds, that's another picture. Good. What can you tell us about DDoS attacks against protocols higher than the 4th level? Well, actually, I've been expecting this question, but we, as network engineers, can only fight attacks of lower levels, some slow attacks that pump out some resources into WAF filtration, and that's done on the side of the administrators, and that's their responsibility. Yeah. It's not done by network engineers, of course. And there's another question with some kind of advertising. Did you try FastNebMont? Well, we read about it, but we didn't test it. We didn't try it. It didn't suit us when we read about it. I can't tell you why right now, but if this person shares his or her contacts, then I can debate this with this person. I can answer. I can give an answer to that. Yes, I'm ready to write my contact details in the chat. Well, there are plenty of questions. We still have time, so please ask your questions. Are you planning to sell your solutions to other people other than your own clients? Well, I'm not authorized to give you an answer. We haven't planned this yet, of course. Right now, it's an internal development, an internal product that we are using within our project. Well, there's another question regarding the 7 attacks, but maybe the answer is the same as for D4 attacks. Well, let's wait for another 30 seconds. Don't get disconnected. Please stand by. Maybe someone is finishing writing the most interesting question. Well, I can see that we have Pavel Odintsov right now, but well, let's discuss it in the chat. Now let's finish our Q&A session. Alexander, thank you very much for joining us. It has been a real pleasure to talk to you. And we are moving on to our next speaker. Our next speaker is from Italy. He contributes a lot to the open source. He has a lot of draft solutions, and he does the BGP monitoring protocols. So this is Paolo Lucente, and he will tell us about the BMP protocol.
Hello.
Hi. I should share my screen right now. Yeah, that's correct. 1 second. Technology is not my forte, so.
Cool.
All right. Fantastic. Hi. Let me see. Okay, perfect. So, hi, this is Paolo, and I am from NTT. And today I would really like to speak to you about, BMP, the BGP monitoring protocol. And, this is really in my opinion, one of the best kept secret at IETF, right? And I would like to share it with you. And I would like to share with you also what are the unprecedented opportunities that BMP gives in order to streamline BGP data collection. Before starting, a little bit about myself, in case you don't know me. I am Paolo. I work for NTT, and in NTT I specialize. I work for NTT, the global IP carrier division, and there I specialize in telemetry collection, every sort of telemetry, streaming telemetry, NetFlow, SNMP, and things like that, BGP collection and things like that. And telemetry has been a little bit in my DNA forever. In fact, I would say I am also the author of a tool, open source tool called PMSCCT, which it's a well-known NetFlow, IPFix, BGP collector. And I am also, a contributor to standardization and community forums, and because of that, I am also here. And yeah, of course, why having the same name on every social media? It will be too easy. Before starting with the specifics of BMP, I wanted a little bit to give you contextualize, where BMP stands in the world of telemetry, network telemetry, and network analytics, and also what will be the scope of this presentation, right? So first of all, let's contextualize BMP in the space of telemetry. Like you can see, I hope you can see also my mouse pointer here. So essentially, you have, it's a BMP. It's just a little piece, and focuses on the control plane collection, data collection, but of course, you have other planes. You have the infrastructure, you have the forwarding plane, and things like that. So you see, it's a multi-dimensional space here. So BMP is control plane data collection, and then on the vertical part, essentially BMP is just a, let's say, a protocol which is developed. It's being standardized inside IETF, and it's only protocol for collecting data. So it's between a monitoring station and an exporter, and the exporter typically be, a router in the network, right? And so in this, vertical space, like after collection, of course, you have, messaging bus. So you have a whole streaming pipeline. You have a big data. You have, UI and things like that, right? So this presentation will be focusing only on BMP, and so it will not cover the vertical or the horizontal. It will only focus on BMP, and it will, also, it's a little bit to familiarize you with the protocol, with the super basics of the protocol, a little bit of history of the protocol, and so how things went at ITF and where we are right now, since there has been quite some, standard, I would say, drafting effort around the protocol, right? So what is one of the most praised qualities of BGP? I would say we can answer that one of those qualities is scalability, right? So it can scale, and we can run the whole internet, over BGP. But how can we do that, right? And that is by applying information hiding, right? You knew that there was a catch, right? So already a couple of slides back, you knew that, it's not that you can achieve, huge scalability without trading off with anything. So essentially, that means that the challenge, the main challenge when it comes to monitoring BGP is, a challenge to visibility, to gain visibility, the maximum visibility possible, right? And so many years ago, and so that would be like almost around 2013, if I'm not mistaken. I was, with the very good friend of mine, Elisa Jasinska. And so one night we were at her place in Krakow, and, over a jar of nalewka, sorry for my pronunciation, which I was, informed that the nalewka, it's the real thing, right? So you have nalivka, which is by, works by maceration, and nalewka, which is the Polish version, is the one that works by infusion. And so by working by infusion, it gives, the highest amount of happiness at the end of the jar. So you see by the end of the jar, very red puffs and lots of happiness going on over here. And that's so essentially what we, conceived a little bit with Elisa that one night. Is that, she was working back then at Netflix, just as a small, detour. The Netflix network back then was like lots of islands, so not a proper backbone like, interconnecting the whole world and things like that. A lot of egress traffic, and these islands were configured, of course, with BGP multipath, right? So lots of transit connections, lots of egress traffic, and you want to try to, have, load sharing, redundancy, and things like that. So how, we were back then, just BGP peering with PMSCCT with, the edge routers. And, we had a problem because you have multipath, and, with BGP, you get only one single path, right? And so what we did back then, we resorted to the only available mechanism that was available to us, in 2013. And you can see the slides, in here in the middle section, couple of the slides that were presented when we presented, at NANOG in Seattle in around those years. So that, the only thing we could do was to enable one feature, which was add path, which was not enabled, in the production network, and we had to add it between, the edge router and the collector, just for the sake and the purpose of, getting visibility, right? And so essentially, it's like, by not having a well-formed monitoring plane, which would be, what one of the addition that, BMP introduces to the picture, right? So you don't use the protocol itself. So you don't use a protocol to monitor the protocol itself, but you have a separate monitoring plane with BMP. So back then there was no monitoring plane. So you have on a production router to add a new feature just for the exclusive reason of monitoring the network, so not to run the network itself. And so back then we were also trying, to add, you can see there was some efforts around the BGP path marking. So yes, around the BGP path marking, which was marking the paths in add path. Unfortunately, that work didn't go anywhere. And you can see on the right-hand side, of the slide that, we were starting to allude to the presence of BMP, but the truth is that, BMP was not really there yet. Like it was high in the standardization, but no vendor was really implementing it. It was not actionable in any way. And what was our goal? Like you see it at the bottom of this slide, is precisely what I said. Like you have multipath and you want to, avoid screen scraping, essentially, right? So more recently, what happened? More recently, we have BMP. So we circled a little bit around, and now finally we go into the core of the presentation. So BMP is the BGP monitoring protocol, and you can see that it has been awarded an RFC 7854, and it had quite a long history, I would say, as a protocol, right? So it was really started to be standardized in, it started the drafting process in 2008, and there was some work until 2012. Then there was a lack of interest. And then essentially, why there was a lack of interest? Because I think there was, something happened in the meanwhile, right? So I would say between 2008 and 2000, maybe 15, 16, which is when, it started full traction and got, the RFC and things like that. I would say many things happened, including like there are now, there were the dissemination of, there was a whole big data movement. It was possible to store a lot of data, to collect and to store and to make actionable, large quantities of data. Maybe that was not really the possibility in 2008. And so, there was a whole change of landscape that I would say there was a revived interest in, security and, with security incidents and root leaks and things like that, right? And I must say that, the original purpose, and we will see that in the following slides, the original purpose of BMP was security and security only, and that was the only thing in mind. So I would say that, if we should speak really the super basic features of the BMP protocol, it's that, it is really an uncomplicated, it comes with an uncomplicated protocol design. And we have to do 2 thumbs up to that, because, it's not, it's not given for granted that you can, build a protocol, you can build, a monitoring plane, and, without complexity. And that uncomplicated protocol design, it is something that is very well defended at IETF, right? So there is always the temptation at some point, an example of uncomplicated protocol design for BMP would be that it's totally entirely unidirectional, right? So the monitoring station, once the connection is established, never speaks back anything to the router, right? And so that's extremely simple. And that the simplicity, like, it has been, challenged a few times, like, oh, let's add some sort of capability, like, there are extensions to the protocol, so let's add some sort of exchange of, what I understand and what you can send me and things like that, right? But fortunately, so far, this uncomplicated protocol design has been defended very, very well. If you ask me, another great feature of BMP when it comes to, monitoring is the fact that it does timestamp. Whatever message the router sends, upon sending it over to the monitoring station, it gets, a timestamp, right? And so that is, something I would say totally huge, like, that just by regular BGP peering with the router, you can not have. I mean, you can have a timestamp, but it's the collector applying some sort of timestamp to the message. Of course, let's say, as I was saying, BMP was a great effort, but there was increased hunger of data, and the original scope of BMP was kind of limited for what people wanted to do back then in 2016 and more recent years. So if you are totally not familiar, and so before getting there, so to what are now the recent works, the extensions, what is happening at ITF, let's really review the super basics of BMP. Like we said, it's a time-stamped, it's a uncomplicated protocol design, but what does it do? And I will reuse slides from Randy Bush, 2 slides from Randy Bush, which totally capture the situation in a very clear and concise way. So when you have a traditional BGP monitoring, like you have a peering router, and there are a number of routers that are exporting paths, like 5 paths. Essentially, when you have a vantage point would be like a monitoring station. Then you get only the best path, right? And all the others, they are hidden to you. But then now with the BMP, you get all the paths, you get all the 5 paths, right? So one may say like that you can achieve the same also with the BGP add path, right? So which is what we were doing back then with the ELISA in 2013. So what is the advantage here? So the advantage here is that you achieve exactly the same, but on top of that, the peering router here would tell you also that the path 0 was received by peer A, the path 1 from peer B, and things like that, and timestamped, like I was saying before. So there is a clear, advantage, in using BMP for, monitoring the BGP protocol compared to just using add paths. In fact, what I would say that add paths and BMP nowadays, they don't even compare to each other, right? So you really send add path messages encapsulated in BMP, right? Because essentially you still want to achieve that, add path sort of, behavior, but at the same time, you want all the nice frills and extras that the BMP protocol, offers you. So let's say what was, one problem, right, with the original RFC of BMP. The original problem, so one of the problems is that it was covering really only pre and post policies ad ribbing, right? So we remember that, in the workflow of BGP, we have like ad ribbing, we have lock rib, we have ad rib out. So BMP was only focusing on ad ribbing before and after the policies. Why? Because we remember that, the main, let's say, focus of BMP back then was security leaks. So it was like, doing a little bit of policy validation, seeing what the cosmic trash is hitting your router like as pre-policy, and maybe you are never going to see it because you designed the best policies ever, right? And so it's a little bit to get visibility into that, do the policy validation and things like that. But still, what was the problem with, with the limitation, let's say, with the original, RFC, is that, still, if you want to get visibility into lockrib for any definition of lockrib, because we will see later, what I mean by that, still you would need, actual BGP peering. And, for visibility in Azribout, you would still need screen scraping, right? So now you have a protocol which brings excellent ideas, but at the very same time, brings, doesn't solve all the problems that it should solve, because you still need screen scraping, BGP peerings to get visibility in other, stages of the BGP workflow. So to visualize a little bit, the problem statement, it's like we have BGP peer A and B, and we have, let's say, filters and policies and things like that. And so what we can get is visibility into the pre and in the post policy for BGP peer A and B. But then, let's say, what really we want to achieve, right? So let's say that in the previous slide, we got visibility into this, but we now want to get visibility also in all of this other part, which is marked with the red arrows, right? And all of that, was totally, undisclosed in the original RFC. So essentially, what we proposed was to extend the BMP to Azribout. Azribout, of course, pre and post policies, right? And that went very well, and we got awarded also an RFC. So that's done and dusted. That was fantastic. I think it was really no-brainer in the sense that, from at least a standardization point of view, working on Azribout, it was very similar to work to Azribin, also in terms of, options, features, and things like that, flags and things like that. And for the lockrib, we made another, drafting proposal. And this one, although, we really went in parallel, like lockrib and Azribout, like really I would say the same day we filed both proposals. The lockrib is still lagging a little bit behind. It's still in last call. It's very good. It's in last call, but that tells you that it's taking much more time. And why it is taking much more time? Because of course we for a long time we remained a little bit on the topic of what is lockrib, right? So it's lockrib. It's just a BGP view. Do we have local routes? We have redistributed routes. So what is local rib, right? So and I must say that the end outcome, since we were hitting also a little bit of vendor dependent, situations, like especially when you touch the relationship between rib and fib and things like that, was on purpose a little bit to leave it to the implementation, what lockrib really means. What are the use cases for lockrib and Azribout? I would say a lot of use cases. I would say I will mention only a few of them here. It's like for the lockrib, so something true to all of them is, the policy verification. So it's true that you can go at any possible stage in, in the workflow of BGP, and you can validate your policies, and you can validate how attributes are preserved or not preserved, right? So, and that is something, in my opinion, great and fantastic. Then specifically to the lockrib, I would say we have, the possibility that we can correlate with NetFlow and IPFix. So imagine that you have your flow and BGP collector, and that is correlating the two. Now you can use BMP, and you don't need BGP peering for that and BMP for other things. And then Azribout, it's also, closed loop kind of, operations, right? So a little bit SDN and things like that. So you have a way without using screen scraping and things like that to check how are your output policies, what you are, advertising to your peers and things like that. So then we have a problem statement number 2, which takes us to the most recent developments of, within the GROW working group at ITF with regards to BMP. So you see here, like you have 4 legs, like it's like we had a table, and this table, had one leg shorter than the others, right? And so this is the best visualization of what we try to do. Fix the table and make all the 4 legs the same size. Why is that? Because BMP has a number of message types, right? Where some, like initiation, termination, they are functional just to the BMP session itself. Then you get the peer up and peer down when the peers or of the peering router that is that you are monitoring are going up and down. A little bit things that you could get through SNMP traps, but of course with much more information. Then you have the statistics report, so a number of statistics that the router can export. And then you have the key message, the route monitoring, which is essentially, and that's true also for the peer up and the peer down, right? So essentially what BMP does is it's embedding BGP messages inside the BMP body. So you can decapsulate the BMP message and parse it like a BGP message, right? So that said, so we have these beautiful 7 types. And so what was the problem? The problem was that not all of these messages, actually even the route monitoring message, which is, as I was saying, the key message probably in BMP, because it gives you the BGP updates and visibility into all of those and things like that. It's not, it doesn't feature TLVs. So TLVs at the bottom part of the message were not allowed. So this is a key feature because, having TLVs across the board of all the messages then allows you to carry whatever extra information and makes the protocol much more useful than just carrying, giving you visibility into the BGP message and things like that. Yeah, you get the statistics and whatever, but with this, you can unlock many more other applications, right? And the other draft that we have going on, it's building a little bit on the TLVs. So with the previous draft, we were trying to build a uniform basis. So every BMP message features TLVs. And with this, we propose to extend the TLVs by the use of enterprise-specific code points, right? How we do that, if you are familiar with IPFix, we do it in we are proposing to do it in the very same way. So you have the so-called EBIT, right, which is a bit in the TLV type code. And if the EBIT is set to true, then essentially before the actual value of the TLV, you have a PAN. A PAN, it's a private enterprise number, right? So essentially what you are saying, you are virtualizing the TLV. You are saying that this is not the standardized space, which would be, without any PAN or PAN 0. In reality, it's PAN null, not 0. That's the standard space. But with this, essentially, you extend it to be enterprise private. So I don't know, PMSST or Cisco or Huawei or Juniper, they can have their own private space and their private code points. They don't have to squat the standard space to carry their own information. So while the previous draft, the TLV draft was, let's say, it has been a working group accepted, there is still a little bit of, discussion on this draft for very valid point, I would say, because essentially what is, what has been the conversation so far was that, we are at ITF and we focus on standardization, and now we are opening a backdoor to not standardize things, right? So it's being a very interesting conversation. My personal position is that you can always standardize things, but up to a certain point. At some point, you hit vendor-specific thing, and precisely for those things, you need, this sort of enterprise-specific code points. And I will go to my last slide before, concluding, before, saying goodbye, which is what are the use cases for TLVs? I would say endless use cases. We identified two for which there are already two drafts. So one is the BMP path marking, right? Well, which is essentially, imagine that you have, like we were saying before, you have, add path enabled BGP messages inside a route monitoring message in BMP. And imagine that you start annotating these paths that you are receiving, right? And you start saying, they are, all active paths, right? Or imagine that you are not getting the lock rib, or you are getting the add ribbing post policy, right? So maybe you have not already the well-formed local rib, right? And there you can have also backup paths or inactive paths or whatever. And so imagine that you are starting really to annotate all of these paths and their roles as they stand in the router. So that's very interesting, very powerful. And the other, which is as when we made presentation number 1 about lock rib and add rib out, so back in, I think it was 2017, the first question that we received was like, okay, now you are giving me visibility in all of these vantage points, but what is filtering, why something is being filtered out and things like that. And so there is a draft also about that, so giving visibility a little bit in the policies and if they are filtering out something and things like that. And with that, I thank you very much for your attention. I hope it was any interesting. I don't know if there is any questions.
Thank you. So nowadays, BGP protocol looks like a Swiss knife. You can do everything, just create some new TLVs. So
yeah.
Unfortunately, we have no questions in chat. So thank you for your story about BMP and also about Nalivka. Yeah. It seems it's time to go to Russia and check it here.
Absolutely. Yeah, that would be my very pleasure. I'm very sorry that I cannot be there this week. It would have been a great pleasure.
So thank you.
Thanks for. Bye.
Дорогие телезрители, сейчас у нас будет перерыв до 15:00.
Dear audience, now we are going to have a break until 3 p.m. and we are waiting to resume our conference after the break. Thank you. The time is 3 p.m. sharp, and we are continuing our next hub conference, and the next presentation will be about segment routing and its application. And our presenters are Boris and Alexander. Boris has recently joined our team, and you could already listen to Alexander's presentation at the previous next hub. Let's talk about segment routing and its data plane, but we will also touch upon other issues. Let's listen to how you worked together. Thank you, Andrei. Good afternoon, dear colleagues. It's very nice to have such a big audience here. It's after lunch now, but we still have a big audience. Thank you very much. My name is, once again, Boris Khasanov, network architect, as I already said. So we are finishing the introduction stage, and now we are moving on to the next one. You probably heard about this technology, segment routing, because any vendors conference can't do without this point. Some people have already tested this technology, so I hope you are aware of this technology. In the second part of our presentation, Alexander will tell us about how segment routing is used. So, people started talking everywhere about this technology a lot of years ago, back in 2013, and you've probably heard about it. But before talking about this technology, we need to understand why should we have it. Right now, we have the normal IP forwarding and the classical LDP, and we have two different protocols, such as RCVP and RFC. And we've been using these two protocols for traffic engineering for a long time. They have a lot of positive features and advantages. I'm not going to list all of them right now. You are well aware of all of them. But they have certain limitations as any other technology. Talking about the LDP protocol, we always have to build a tunnel via the protocol for dynamic routing. So traffic engineering is quite problematic in the event of LDP because you will need to face metrics, and there is a lot of noise as well, and you have to synchronize different things there. As for LSP and TE, which enable traffic engineering there and choose the shortest path, those methods already have some limitations. That is, the need to support forwarding state at interim devices. And the next point is that there is a dependence on the number of LSP. And this depends on the number of PEs that we have, which is not convenient either, particularly if we have a lot of PEs. To conclude, it's quite difficult to configure these networks manually. So instead of trying to respond or to find a technological solution to these issues, the technologies of segment routing was born. It uses source routing, as you can see on this drawing. And you can see that our incoming PE or ingress PE determines the number of packets along the path, and it adds labels to those packets. And in the simplest option, one segment is enough in order to get from the source node to the destination node. And this segment is a kind of tool. it's about the topological feature. And as we talk about segment routing, something that we can simplify by doing LDP and RSPTE. So we first use those segments for LGPs. That is the additional expansion to other mechanisms. And to be very brief, I don't have much time, but I would like to remind you about the types of segments that we have if we use segment routing. First of all, it's probably the basic segment. Prefix or node segment, which is unique. It's either prefix or a particular router are determined. And as I already said, there is the IGP expansion that we use. There is also a technology or a method that identifies the router's interface. We can identify a segment which is connected with a specific router's interface. There is also another method which is pretty convenient, and this is called Anycast. And there is also the binding SID. This is probably the most multifunctional SID, which has a lot of features. And I'm going to talk about one of its applications. And there is a type of SIDs which are connected to BGPs and which are used in architecture where we need traffic engineering between different autonomous systems and design on this basis. What segment routing can we have, colleagues? There are different types of segment routings. I can't tell you about all of them, so let's focus on two most important ones. The first one is MPLS, or SR-MPLS, at the forwarding level. And this routing segment is similar to our favorite MPLS. This is where SID is passed on as an index or an absolute value. That depends on the vendor's implementation. It has the format of an MPLS label. It also supports all the features in the classical MPLS, which is set on this slide. And furthermore, we can have a best effort, SRBE, that is the shortest path, and there is also SR traffic engineering. And there is another important branch of segment routing development, which is called SRv6. And it is different from MPLS because we do not use any MPLS at the forwarding plane. And the prefix SID is an IPv6 address. In case of traffic engineering, there is another heading or routing header, which is called SRH for SRv6TE. And this is where we write down a stack of our SIDs. And the first SID is going to determine our next hop. And this is how we run through all the routers that we have in the network. And there's a key moment which differentiates SRv6 from the other system, is that its SID consists of two parts of varying lengths, the locator and the function. And I also included some backup slides at the end of my presentation which showcase those functions. This is how the segment routing is working on the level of forwarding. If we need to transport the traffic from PE1 to PE5, and if SID 16005 is generated, then it goes back to PE1. And then there's VPN 16005, and it goes to PE5. If there are two paths with the same metrics, then there will be a hashing towards those paths. The traffic will be transferred via the same path. If we have traffic engineering, we should add a configuration. We should describe the explicit path for our router, or somebody has to tell us about it, some external system. There is a difference with SRv6. Those identifiers SID, you have some brief information about them below the slide. Those identifiers are able to give a unique identification of a router with this SID. They will tell us that this router will interfere with our package somehow. And we are going to flood this SID. And at the forwarding level, you can see the 6 PE, and there is the VPN SID that we have at the exit level. If we have a VPN network, the packet goes via our nodes, and then you can see the next SID, which is copied to the destination address, and the count of the number of segments goes down. Here is a short description of all those technologies. And you can see here on this table that there is a difference between those technologies. You can see whether it's easy to program all those technologies or not. I'm not going to describe this in detail. And of course, we all bear in mind that we might have a good possibility to pass on the traffic via the shortest path, but we still need traffic engineering. In the classical solution, we have a system that signals how to dispatch this data and how to distribute the labels. But how do we organize traffic engineering? The first attempt of implementing traffic engineering is a mechanism which is called flex algorithm, or flexible algorithm, or flex algo. The idea is to calculate different options of possible paths based on an algorithm definition. Some additional metrics are used for that. Thanks to the IGP protocol, we can build different paths, and they can have different values ranging from 0 to 255. There are different SIDs between the paths, and as a result, depending on the service, there will be one or other topology. So this is the next step towards traffic engineering. It looks pretty interesting, and Alexander will tell us about it later in greater detail. But if we need full-fledged traffic engineering in its classical meaning, we need to have an exterior mechanism that would read those complicated topologies. We need to calculate the topology, and for that we need the PCE computation element, which computes the optimal paths, and it works with traffic engineering database. And it's important. We'll see why. I'm not going to tell you about PCE's advantages. It's the offload of routers from heavy computations. The routers become clients based on path computation clients, PCC. There are coordinated computations and so on. But the key question is how to get this traffic database device or controller, which describes our links within the network and the limitations that we want to use. So we can get them from the link state database or from the outside. If we get it from LSDB, we need our controller and PC functions to have interfaces with all IGP domains where there is a major issue. But this solution is not really scalable. The other option is to expand the BGP protocol, which is called BGP Link State. I'll tell you more about it later. And we can have the traffic engineering database via the PCEP protocol. The industry currently uses both approaches, but the most common one is called BGP-LS. Here you can see more information regarding BGP-LS. There's already RFC, and your link state and LRI, which describes the link, and we also have some other systems. And there is also the PCEP protocol. That's the second type of PCI, which works with the routers, and the protocol works on top of TCP. The routers become the clients of PCEP computation clients. The servers interact with each other, and the most important thing is computation request and the report, in which the controller gives the computed path to the router. And that's not all of it. It's good to have a PC, but it's not enough. Ideally, we need a structure with a more complex hierarchy based on traffic engineering. And this more complex hierarchy is the SR policy. This is a structure which links a number of segments, because our traffic engineering is determined by a number of segments. So this structure links those segments to the specific target or intent. And there are three parameters which characterize the SR policy, which are called headend, color, and endpoint. And we have some candidate paths here. And you can see the SR policy at the bottom of the slide. We can see different paths or candidate paths here. There might be many different candidate paths. Each of them has a certain preference level. Some of them are more preferable than others. And it's important to do balancing, both equal and unequal balancing. Compared to the classical TE, you can see the differences here on the screen. Last but not least, this is where I would like to finish my introduction part. That is the technologies that decrease the probability of failure, such as MPLS or another technology. And we have the LFA topology there. I'm not going to tell you what it is about. Most of the listeners are aware of this technology, but we need to move this traffic to the next hop so that it doesn't get back to us, because we don't need this traffic. And this LFA technology uses the topology-independent LFA and the construction of a tunnel. And it also has a list of segments which will be delivered to the router that will not send the traffic back to us. And it works even in the most complex topology, where RFA or LFA does not work. So this is exactly the technology that functions well in combination with segment routing. But it's noteworthy that LFA and the SR policies I mentioned do not work together. They don't know anything about each other. So the best backup path should be used within the SR policy.
And the last slide, because I'm a little bit behind the schedule. This is an option of using the binding seed, which I mentioned from the very beginning. This is when we can use that under the slogan mirror seed. So this is the same binding seed, but this is how you may protect egress PE. When we see that BE3 wants to back up PE, we actually do the mirror seed, and it mirrors that start flooding, and so it means that PE3 will protect PE2. As soon as the routers would get this announcement, this statement, they would make the fast read around on the redundant next hop with an indication of PE2. So once something happens to PE2, we don't any longer have to update the egress PE. We can immediately, at the level of P, switch the traffic to the second PE. So this is the idea behind that. So the binding seed can be used in order to protect egress PE. This is also being used for SR policy protection. With that, I have to conclude my remarks, because I have run out of time. I would like to pass the floor to Alexander Klimenko, who will speak about the second more important part, the place of SR in Yandex network. I'd like to thank Boris for getting synchronized. We'll now understand what options of SR are available there. My name is Alexander Klimenko. I'm doing a lot of interviews for Yandex, and very often I'm asked about control of the network. iBox in the network will manage to answer the very first question only, probably not even exhausting the question. SR implementation is no longer a testing or pilot project. And the main idea of my project is to show the route which we have made, to showcase certain problems we run into. Probably it will help some of you to solve the same problems. I will show how DSI looked before, what helped us to start the same project with the segment routing. Before, actually, we had more than 100 devices within PE, based on a generic chip, and whatever you do for the operational system, this chip will not work better, and the structure, the hierarchy, leaves much to be desired. And we certainly saw the problem with the folding, with compatibility. All the sources started with the spine of the first year. So one more popular question is whether you have common data center. We used to have it, so everything has changed, and we actually outsourced the edge port routers, and the services start from there. Therefore, we can develop from that, and we can use SR using the old equipment. The second thing is how we divide our topology. We used to to say that we have fastbone and another type of network. The division of these processes is done using two different routing processes, so that the traffic goes to one of the topologies. In the announcement, actually, we put either backbone or fastbone topology, depending on the address. In the traffic engineering, we already have ESRP. Why traffic engineering is needed? It is because actually you get connected to the network kernel, and that's it. Now we have data-centric channels and links, and we have foreign channels as well, and DC connections are no longer sustainable, and we need some control within the backbone. And this is a nesting doll. The services of 6P, 6LPE on top. And there is a standalone piece of fastbone network. Why we need SR? Just to get rid of state from the old boxes, to mend the topology, make it more regulated, to disseminate the traffic into different links, and to use the links differently. You don't have to think that once you engage SR, everything would work smoothly. What we saw, actually, we looked at SR MPLS versus SR V6, what to choose. 6 months ago, the vendors did not provide for the compatibility. And in terms of the operational standpoint, the transition from stack to MPLS looked much better. Therefore, we solved that problem quite easily. Actually, we thought about dividing these routing processes. We thought whether to divide that into fast bone and backbone, but we realized that probably this can no longer be used. Let me draw an example. One of the vendors of the network equipment implementation of the second option is separate or standalone logical router, and it would get with the special stamp. Certainly, it can be redone and it won't be overcome, but this approach is no longer the best and the most optimal. Therefore, probably the division into two processes is no longer applicable, and we can use either SR without TE, but there would be a problem with fastbound. It lies in the head that however many links you will give, it won't be just marked. From time to time, we'll see the picture like the one on top bottom, on right bottom, when the whole band will be occupied. Next option, we'll speak about the division of the networks. So we're speaking about QoS-based approach. Several tunnels are being built. One of the tunnels actually would have one kind of DSCP, and the other tunnel would be engaged with the different kind of DSCP. The disadvantage is that we'll have to control all the nodes within that network, and probably will not resolve that problem until the end of this year. So, for instance, the machines within the data centers, so they want to download the software, and you have to control the DCP. You decided to update some switch in the lab, and you have to control the ink. Therefore, this QoS was not applicable. The approach when you use some single process for backbone and not to use that for fastbone is not an option because it will overload the network. The options, everyone who is fond of SR may remember, this is SRTE and FlexAlgo. SRTE similarly suits us very well because it is very simple, very native, but the tunnel between two PE units could be built only to one seed node. So it means that we have certain address of PE unit which is being used as the router ID, and we give node seed to that. You build the tunnel to that unit. Once we give one more O back and one more node seed, then some vendors did not allow to build one more tunnel, and so this was not an option for us. FlexAlgo is a super thing, and hopefully, similarly, this was our case. When you define topology, you build certain SRT channels within FlexAlgo, but it turned out that the vendors do not support 3 FlexAlgo topologies. They only planned for that. So what we came up with, we are using a SR policy. This is a thing which looks very much TE, classical TE. Between 2 pairs of TE, we would offer 2 kinds of SR policy, one for fastbone, the other one for the backbone. We're using segments of sheets, and within the policy we have CMP up to 8 paths, which we're using. Certainly, it's not very convenient to do that manually, but I will not have time to tell you more about that. Also, this nightmare embraces our other routers. Another problem we are facing is that not all the vendors believe it is necessary to update the routers even within the segment sheet. For instance, if the neighboring station fails, still this policy remains valid. And to conclude my presentation, let me tell you that SR is no longer just want to have technology. It's being released for quite a while, and we are not an exception. But you don't have to think that SR can be installed at your network with no efforts. I invite you to start doing that immediately and approach the vendors. You are the clients, the engineers who are defining the vector of the technology. That's it. Thank you so much. Thank you so much, Mr. Klimenko, Mr. Khasanov. We are behind the schedule a little bit, but it is worth doing that. And some questions. I think that it is a very interesting topic. First question goes from Roman. As expected, condition is not forward in low-band internet. Don't you think that SR over EDP is more attractive for the use of internet? If you are speechless, then please unmute your microphones. Apologize. I muted my microphone. In terms of SR over OIP, has been written the RFC. Actually, we didn't have time to speak about that. They have their own advantages and disadvantages. But first, look, colleagues, I understand that when we're speaking about the technology for tunneling technology and overlay structure, we are speaking about more local spectrum of application. We are speaking about our own or corporate network, which is controlled by us from in out, and we're responsible for that. Probably in future, there will be similar global networks, but we employ a local scope where this is not a problem for us. Okay. There was a question whether Yandex is using SR and SRTE. There was a question about the multicasting and VPN, so let's skip it, because this is not our case. We are not speaking about multicast. And just a brief comment on that. Multicast, this is a separate technology. And SR, this is a standalone technology, and would need either beer or beer with. So the chat members also speak about beer, and there would be discussion with Jeff Tansura, who actually also is very fond of beer and beer SF. So one more question I will skip. Question about what kind of employee seeds are there available in Yandex. I think that we have exhausted the questions. I think that people are very much moved by these topics. Only we are controlling that. And that cost topic actually is a very big story for us. In the light of the year, we cannot guarantee that nothing would happen. We have TOR where we would mark something, and there are security LCR there on that TOR, and all of a sudden it goes into the same TCOM memory. So if something goes wrong, the traffic would be unmarked. Sometimes it may happen, so we could not guarantee at that moment that within a year's time everything would be good and 100% controlled. Okay, and the last question for today. Have you ever run into the depths of stamps at the current hardware? No, at the current hardware, we don't have such problems. We have enough stack stamps, and it would be done by a smart device. The H-code routers, which are doing only pop-up stamps, and there is no problem like that. A brief comment or some addition to complement what has been said. Even such problem arises. We have the notorious bind seed, which helps us to address that problem. Thank you. Thank you, Boris. Thank you, Sasha Volk. I think that this topic was very interesting for our viewers, and guys are waiting for us on chat, and we are proceeding with the second presentation. Some exotic things for networks, because this is not so popular topic. We're speaking about distributed ML training and in-network compute. I'm passing the floor to Dmitry Afanasyev. We'll speak about the network, which is used not only to send the packages, but also to do some computation. Dmitry, over to you. Hi, everyone. Can you hear me well? Good. Just a second. My name is Dmitry Afanasyev. I'm a network architect of Yandex. I will tell you about a very exotic technology, which I think will become less and less exotic, more and more popular. So, saying that, let me highlight my topic as distributed machine learning technologies and in-network computation. Let me briefly tell you what neural networks are about, how they function, how they are trained. We'll speak about the distributed distance learning training, how traffic patterns look like, and how they can be laid over interconnect topologies. And last but not least, I will speak about in-network compute implementations. Before I proceed to the topic at hand, let me tell you that the progress goes to the fact that the network which lies in the middle, it has to be fast, simple, inexpensive, and fault-free. But any rule has exceptions. So there are some specific applications which computation system and the data exchange system look like that once you do some computation on the network, you may optimize these computations, and we'll see how the goals and problems look like. And you can add usability once you do computation in the network. So what neural network is about? So you may see a biological neuron on the left-hand side, and on the right-hand side you see the mathematical model of this neuron. It's structured very easily, so it has ins, which receive certain signals, and there are some scales, and there is a distortion inside. The vector of inbound activators is being complemented by impulses, and this goes to some processor which gives an outbound signal. And it means this system has to be monotonous, homogeneous, and modified, because this is how the training looks like. The same thing, but in more detail, with their equation accompanying it. You may see that here we calculate the classical weights connection, and these neurons make up a neural network. It has an inbound level, which doesn't do anything, but acts only as a receiver of certain inbound messages.
And then there are several layers on which this information is processed. There are input and output layers, which we call And we also have some hidden layers, which are not input or output layers. There can be several different hidden layers, and the neural network can have this structure. The structure is not chaotic. We just process something in one node, then it is passed on to the next node, and so on. And we will see how the machine learning is happening. And finally, neural networks have two different modes of functioning. There are two methods of doing something with them. First, they have the inference mode. That is, this network works like an ordinary network. We provide some input data there, and it gives us the output. This is what is called inference. To get some networks which will do classification or some other useful things, we first need to train the network. That's the training mode. Those modes have a different number of calculations and data. Inference is done with a small amount of data. Training is done with a large amount of data. In it, the data moves both backward and forward. There is a direct path. We get the result. We look at the errors, at the deviations from what we are supposed to get. And then we send the information about this error back so that the system adapts to the new situation. As a result, learning is all about risk minimization. As a result, we do have a resulting function from this neural network and the data that we would ideally have. The difference between what we wanted to get and what the function gave us is a loss function, and we want to minimize those losses. To minimize them, we use the stochastic gradient descent method. In a neural network, there are many neurons, many connections, and when we present this network, we want to minimize the losses in every neuron of the network, which is a difficult task. As for gradient, we choose a big learning selection, and based on that selection, which should be a big selection, we can minimize the losses. If it's a small selection, then the network might make mistakes or learn badly. It's not necessary to use the full set of input data all the time. We can use a certain set of this data, then we can do the computations, and it will be a pretty good gradient as a result. Thus, we do not take the whole data set for every iteration. We take a subset. We do the calculations with the subset, and finally, we have several different types of output data, and when we go through the whole set of data, this is called one era of training, and then we repeat the cycle all over again. In order to calculate the gradient, after we did those computations, we go backwards along the network. We are not going to look at the equations in detail, but this is a very effective method of computations because it considers the network's structure. And this method is called backpropagation algorithm. It is much more effective than if we tried to calculate the gradient by brute force. It takes into account the similar structure of the network, and it uses earlier calculations and computations. The process can be presented as the following flows, the following flow graph. Here we have the direct data propagation, and here we have the backward propagation. This is where the computations go go in the other direction. And finally, the computations should reach those points in the chart that we are trying to optimize. To sum up, the backpropagation algorithm is an optimized method of calculating or computing the gradient. It uses the information about how the network is structured. Then this information is propagated backwards. The derivatives are computed and calculated. And the chain rule for complex derivatives is used because every function in a neural network is based on the previous functions on previous levels. Now that we got an understanding of how a neural network is organized, we can see what happens during the neural network training. We start with randomly initialized weights, and we iterate through our data a mini batch of training data sample. There is the forward pass, the backward pass, and we are interested in training because reference is easier than training because there are no difficult computations there. They are less complex anyway. So the forward pass looks like a path along which the data follows. There's the input, the output. So this data moves along the network, and we get a certain result. If the mini batch has the size of more than 1, it usually has. It's not called a vector then, it's called a matrix. And each interim result is also a matrix. This is what normally happens with the mini batch, and this is effective because a GPU is aimed at working with metrics. Within each level, we multiply the matrices, the matrix of activation, the matrix of input weight, and we get the output matrix. As a result, when we ran the forward pass, we got a certain result. And then we have a value that we would like to have. When we get both of them, we calculate the loss with our loss function. And we get the loss value that we would like to optimize, actually. After having computed the losses, we go backwards along the network. And the goal of this backward pass is to compute the updates to the layer weights and how the neurons in the network should be shifted. So we send information about the error backwards along the network. Every level calculates the gradient of the weight and updates the weights. And each level calculates the activation gradient and gives it back to the previous level. In terms of the structure, the computations really resemble what we had in the direct pass, but the matrix is calculated in the other direction. We go backwards along the network, and we calculate the weight updates. At the input, we have current weights. At the output, we have new modified weights. And the operation is about updating each weight while taking into account the current gradient. In practice, the computations can be a little bit different, but the structure of computations is still the same. What is important is that those computations can use much more memory than the model itself, particularly if some other information, such as current states, is stored in the memory. So this is what we have at each stage of the computations. First, there is the forward pass, where the matrices are multiplied. Then we have the backward pass, where we have the weight gradients and the activation gradients. And finally, we take the weight matrix, we add the update matrix to it, and we get the final matrix. What is important is that all those computations can be done in parallel, because the training task is a very complex one for a neural network. And one way to simplify it is to make it parallel. Without making it parallel, it can take weeks or months to train a neural network, and we want to do it faster. How can we achieve this parallelism? There can be different methods. One method is data parallel, and the other method is model parallel. And the model parallel can be split into the interlayer and the interlayer. Data parallel is where we give different computations to different nodes in the network using different input data. We use different nodes to compute results from different data. If we talk about model parallel, we can calculate different sections within the same layer, actually different neurons. We can even use different machines, or we can use different levels to calculate them at different neurals of the network. Each model of parallelism has a different structure of data flow. And we are going to focus on data parallelism. It is more simple. And this is what we have with data parallelism. Each worker has a copy of the entire neural network model and is responsible for computing a portion of data, or training mini-batch. During the forward pass, it computes output activations for its portion of mini-batch, and no communication is needed. The communication is started at the backward pass because each worker computes activation gradients for its portion of mini-batch, and it computes contribution to the weight gradient based on its portion of mini-batch, after which all workers should sum their contribution to the weight update. Each worker calculates or computes its own contribution only for this particular mini-batch, and then all the contributions are summed up to get the necessary weight update. So, data parallel or forward passes. Here you can see that all the nodes work within the same weight matrix. Here it works with the same input data. Here there is work with different data. And the most interesting is communication. And there is one mechanism which is called all-reduce, which is a typical operation for supercomputers. There are a lot of typical operations. Everyone is aware of them. So all-reduce is one of the most popular systems. And actually, we reduce or get together or sum all the results of interim computations, and then we spread the result to every node. There are many methods of implementing all reduce. Those choices have different expenses, but the worst solution is when every worker gives its results to all the other workers, but nobody does it like this. There are more efficient methods, such as the so-called ring reduction or the one-shot reduction. One-shot reduction is usually used for switches, where all the nodes see all the other nodes, not necessarily via one hop, but they are within walking distance. And those reductions can also work in hierarchy. And there is a pretty big communication overlap here, which grows together with the degree of parallelism. We are going to look at it later. As for the model parallel within the layer or between layers, this is a picture of how these tasks are implemented. So why is it important to include communication between nodes? This is a chart which we drew based on a certain test cluster. There is a GPU power here. The GPU was pretty good, and the other chart is about data exchange. And we can see that our GPU, which is very expensive, remains idle during the exchange of some data. So in real life, we don't want this equipment to stay idle. How are our traffic flows organized, and how are they connected with the interconnectors? A little bit about group and collective operations. And that's where we have one data set, and we give some data to all the other nodes. Sometimes this data is scattered. Sometimes there is a reduction when we bring different pieces together and try to compute something new based on them. An important part of reduction is that the size of data does not change after reduction. That is, we have a certain size of data in every node, and when we summed all this data, we have the same amount of data with the same size, but it takes into account all the other data. A naive one-shot reduction doesn't scale, it's not effective. There are different implementations. For example, the so-called ring or reduce, which boils down to the fact that we have nodes on phase one. This is a closed loop, and all the data, all the results are communicated to the next node. And finally, every node gets its own result, and then it replicates this result to all the other nodes. If we have a hierarchy and different axes of loops, this topology becomes hierarchical, and it goes well together with the classical topology of interconnectors, because here we have indirect or switched networks, which are not directly connected to other nodes, and those nodes are connected to switches.
There are interconnection networks, which are called direct, or which are called P2P or point-to-point, when actually have the computation elements included, and many supercomputer networks and many clusters historically actually are not embedded. And multiple collective operations actually are good for such an interconnect function. And if we speak about the machine learning, then probably Google, for instance, does their own processors for machine learning, and they're also doing some clusters for that. And the TVU clusters topology looks like that, and it allows for the extrapolation of that topology on the cluster, but not everyone can actually do such intertwined connectors. So what can be done? What if switches could also compute something? Hence the in-network computation. We'll look at the two applications. First of all, SHARP. This is an in-network scalable hierarchical aggregation and reduction protocol. The computation in network from Ivanov company, and all reduce example switch to trees, reduce to trees. They optimize the reduction objective, and there is one more type of calculation of reduction. This is, for instance, a tree through which the operations may go. This is a logical tree. It reflects the topology of the network. And if we speak about redirect or switch-based network, then actually it may be reflected incorrectly, causing some overload. One of the implementations of all reduce, this is a recursive doubling. So it goes in several stages. What SHARP does? SHARP, first of all, is based on the following, that within the commutator, we have some logical networks or devices which may do some computation. For instance, it would be enough just to do addition, but they may act with the HPC-based popular data. And in the case of SHARP, you will also build an aggregation tree, that's a logical one, extrapolated against the topology of the network. So what happens? We have some interim calculations, and these data actually would be sent down the tree. And once it goes up the tree, reduction would take place. And certain nodes would assign certain data for the reduction, and the system would reduce the data to 1. So they got several data sets from different nodes. Once you add those vectors, only one vector goes up. This goes to the root of the tree, and the root of the tree would get the final sum, and then it would go up from the root to the crown to the top, and the final result would be distributed on all the nodes which participate in the computation. In that case, we're speaking about seed, and this operation looks very efficiently. This operation would not go smoothly once there are some losses in that network and we had to use certain supports. But in case of a SHARP, it works smoothly. There is another quite important thing. It is not that switches do computation very quickly, but they do a very simple operation. They just do addition, so they're located in the right place in order to do computation. After we added the switches, less data is being passed over to the next stage. And not only we do the write operation, but we reduce the volume or the scope of data which would be transmitted further. For instance, here on that flowchart, we may see how that approach may be used in application to the band. But actually, it's good once you can use that for the latency. You may see that the latency remains the same. Constant, sadly, this is not true. It is a logarithmic dependence and would depend on the number of tiers or layers. See, in essence, this is a multiplicity of tiers, And everything would depend on the number of tiers, not on the number of nodes which are engaged in the computation. Bear in mind that switches are of big size. It means that you may have very good latency even when the clusters are big. But we're speaking not only about the retention or latency and about the cluster size. There is some result obtained when training the networks. We can more specifically say that we may only benefit from the use of Sharp for AI. So bear in mind the modern GPU and how that corresponds to the computation. 10% in the productivity growth may actually pay off the whole project. And one more application. This is not a production value, but it is more affordable because it implies less costly equipment. So for some research purposes, it may be more affordable. And even if you don't have a big cluster, SwitchML looks nice. The same problem. The distributed learning. When you calculate your interim results, you have to aggregate them and do that efficiently. And you want to do that using switches. What can it be done on? Here we may remember that we have programmable chips from Barefoot company. They don't have the floating point support, and still they can work with digits. But still it can be used in order to build a working structure in the net. But it would be labor intensive. It would require certain efforts and would be actually some distribution of responsibilities between workers and switches. Workers would chunk up vectors, would quantizate and scale, because actually floating point has to be moved. Switch doesn't know what else to do. And as far as this is a regular package network with losses, we will have to be able to detect and recover from package drops or losses. Switch will integrate vector addition and count and compare how the operations are done. I will not go into the details, but quantization. We convert floating point. They have different orders or different factors, and desirably, in terms of a scale, it should not have much deviations. An important thing is about the packet loss resistance. So packets may be lost in two directions. Workers should detect losses using timers. Lost packages would be retransmitted. If a switch gets the same package for more than one time, actually it would be just dropped the switches. By means of bitmaps would identify actually what packages are received and would ignore doublets or duplication. Then the whole structure works with a kind of a zoo of technologies, but at the same time different frameworks are being supported, and this is appropriate for machine learning. That's actually the cluster where the tests were done. And here we see that this cluster works much faster. It's a prototype, which is based not on the most efficient technologies, but what is available. And it proves to be quite efficient against the option which does not imply the computation on the switches. Anyway, it would be more than 1, and sometimes even would equal 3. What is so important? The experiments show that the performance does not depend on the number of workers, unlike the options with no computation done on switches, but it performs very well when the package losses are quite reasonable. And 0.1, this is an average loss rate, and 0.01 actually looks better. And finally, let me go into the detail as to how the package loss tolerance is being built. At the stage of aggregation, we ignore duplication, and we are looking for the default, and when the results are disseminated, we open the result, and if the worker has not received the result, then it would resend the inquiry. So the system is a two-way street. Sharp and SwitchML actually are described by multiple resources. They are open source, and the presentation will be available online as well. Your questions are most welcome. Thank you so much, Dmitry, for a very interesting presentation. But please visit our chat, so there were people who were very much interested in your presentation. So it'd be great if you get in touch with them. I will try to do my best to do that. And we are proceeding with the next speaker. With us from California, Vladimir Gurevich. Please welcome him from Intel. He will tell us about the chips which were mentioned by Dmitry Afanasyev, and he will speak about the full language. Good afternoon. Good afternoon, everyone. I do hope that you can hear me loud and clear. Let me share the screen. Hopefully it works. Welcome, everyone. My name is Vladimir Gurevich. I'm working for Intel company as a principal engineer. I'd like to tell you about programmable high-speed commutators and switches. And the previous presentation actually acted as a precursor for me. Dmitry told you where these switches are being used, so the transition would be very smooth. Some nowadays a disclaimer from our lawyers who warn that, and I will skip that, but I just have to show that. What I'd like to tell you about, why these microchips are needed, the ones which Intel produces, and how they may be used and what for. Secondly, let's speak about how to build them, what is inside, why they are now possible with the current state of the art, and let me tell you how it may be programmed using P4 language, and what can be done next with that, and hopefully we'll have time for Q&A. I'd like to start with the following. Network technologies, that's a very interesting thing. On the one hand, people try to invent something new, and there are a lot of reports, both at that conference and elsewhere. People were speaking about some alternative approaches to different things, and that's a difficult problem. Until recently, people thought that no new technologies are needed because there are a lot of generally acknowledged standards. And once you have generally acknowledged standards, why you have to reinvent the wheel? But there are now progress drivers. For instance, large-scale data centers such as Yandex, Facebook's, Google's, major internet providers also give it a try to build something in-house, and governmental offices and agencies also are part of the process. What happens? First, we had a very disintegrated internet. Everyone would be building something on their own, and there was no connection in terms of standards and protocols. But now, the processing done by big centers data centers. And on the one hand, people would need the scale, which they were lacking before. They would need the flexibility. People try to make sure that their problems are solved. Energy efficiency has become a big problem, which has to be addressed. And on the other hand, this centralization allows to get away from the standards and to get off the beaten track to offer something new. From the presentations which I listened to prior to my speech, I only got convinced that people all the time try to do something on their own. But the architecture of the networks are quite conservative, and it is very difficult to think of something new, and it is even harder to bring that into life. A regular software world looks very simple, so once you have certain idea, you just buy a simple out-of-box equipment or facility, for instance, plug-and-play chip, or if you have to, actually, you may buy a regular computer or a virtual machine in the cloud, and there are lots of programming languages to help you write your own software, and that's it. So you can make profit. You may take that to the bank, but in the network world, everything is structured differently. You cannot do anything on your own, therefore you go to the network equipment developer, begging him to do something. And the developer would tell you, you see, these things are good, but in reality, as the previous speaker has said, actually, whatever you do to the box, it will still not perform the functions of a microchip. So you have to actually approach Miranox or Broadcom to develop a microchip to add new features. And they will say, yes, actually, these guys look nice, but usually microchips are developed not only to make it work faster, but it would take a little bit more than 2 years to add new functionality. We are waiting for 2 years, and more ideas will come to us. And we forget about the old idea, and we do something else. We switch to something else. So it happens so that networks are quite conservative, and changes can hardly take place there. The popular wisdom said that either we are using programmable units so they can, for instance, write your own software, but usually these solutions would be several hundred times slower, and it would be more costly, it would be more energy intensive, etc., etc. Here is where Intel may help. It all started with Barefoot Company, the one which brought me to Intel as well. We decided that it's no good. And in essence, this problem is not so difficult, it can be addressed. What observations we made? First of all, the data plane algorithms are quite simple. So we have to change the headers to calculate something, to assign something somewhere, transmit something somewhere, and to get rid of the headers. This is the only thing you have to do. You have to manage the commutator's state. For switch, this is quite easy. Switches would need some external components, and we realized that it is not very difficult to run them. I will tell you in more detail how.
Secondly, and that's also important, is that those operations can be parallelized, and every operation consists of many simultaneous operations, because many fields are processed independently. And furthermore, high productivity is where we can build a long conveyor. The longer the conveyor is, the more packets are processed on it. And most importantly, this should be programmed in a high-level language, because if we do this at a register level or something, then nothing can be done. So how is it organized in real life? It all starts with this abstract picture. This is a protocol-independent packet processing. And this structure works the same for every switch. When the packet goes to your switch, first it's the disassembler or parser of the packets that starts working with that. So this parser identifies the network headers there. It's a pretty simple machine. It looks at the headers, understands that this header is followed by some tags, and then it understands that after that tag there is a TCP and so on. So this parser splits the packet into separate headlines. And we are still accepting the packets. Those packets can be very long, but we do need to process the header. And those headers go to a conveyor, which does the same operation, match action. How does it work? It's very simple. We have a table, and we do a search in those tables. You need to look at the destination address. This will be in your search. Then you need to find the output port, for example. Then you can do something else. Or you can use IPv4 to find the destination address. Then you check the control sum and so on. So what happens here is that this data starts going through this conveyor. And at every stage, there is a new interim result. We remove some of the headers, we add others, and there may be a different number of such headers in a switch, up to 20 actually. And finally, we only have the last 3 headers which underwent all this processing. And they go to a deparser. There, they are put together with the body of the packet, and there are new headers stuck on them, and then this packet goes for further processing. So this is the architecture we have. I hope it's pretty simple. What's particular in it? The packets are only moving forward, which is why the duration of processing is always the same. There are no cycles here. If you need a cycle, then you need to have a loop back in the port. And within each stage, there are many tables, not just one of them. We can do parallel search in the tables. And most importantly, with every cycle, there are new packets coming and processed. It's very easy to parallelize those actions. The bigger the envelope is, the more packets we process simultaneously. How do those tables function? They are real tables. They look like all other tables everywhere. They are rectangular, and they consist of 3 parts. The key, with which we do the match, the action code, that's what we need to do next, and the parameters of the action. Those tables are programmed by your control player. And unlike standard tables, these tables have an additional line that is actioned by default in case the key has not been identified. And then all those components come together linked by a bus, and they are called metadata. Then some fields are chosen that are of interest to us. For example, the destination MAC address or VLAN ID. Then there is the search key, and this search key is composed in order to do a search in the table. And we have two types of an answer. Either we have found this answer in the table or we haven't. And if we haven't, then we used the by default action and parameters. And then there is a small multiplexer which chooses between the two possibilities. And then it goes to the action execution block, where we do those additional actions. And we can use any headers and metadata that are available, and the results go once again to the same bus. And it's very nice because we can work on those tables in parallel. That depends on how much place we have in our microchip, and we can put those tables one after another or in parallel. It's very easy to work with many tables in parallel simultaneously. So that was some abstract architecture, but when we build a real device, we need to have a certain mix. On the one hand, we need programmable blocks, an input and an output conveyor or pipeline. The input pipeline has an input packet, then there is the parser and the depasser of the packets. And in the output pipeline, we also have some operations. And between those two conveyors, there is a packet interface which delivers the data inside the pipeline or conveyor pipeline. And then we have some data which goes out of the input pipeline. And finally, we have a packet replicator and a traffic manager which are in the middle, and here we buffer our packets. And here we can create a multicast to make sure everything works okay. And we talk with these devices via special system metadata. They are well-known variables. If the packet comes out from the input interface, the input interface sends us the time label, and then it sends us the number of the port via which we got it. If we want to send the packet to another port, then there is another known variable which tells the system to send this data to port 5, for example. So that's about it. As for the real microchips, we built the Intel Tofino microchip in 2016. It has 260 ports, 25 gigabits each of them, and they can be put together in different combinations. The frequency is 1220 megahertz. And the interesting thing is that this chip was the same as any non-programmable chip in terms of costs. And we already have Intel Tofino 2, which has a productivity that is twice as high. The technology is 7 nanometers. This chip can carry out more difficult operations. It has more pipelines and so on. The Tofino has 4 pipelines, not one pipeline, but 4. So it's like a 4-core processor, but the ports are linked to a certain conveyor. And what happens is that they have this traffic manager and packet replicator, which are attached to all the 4 pipelines, which is why data can be moved from one pipeline to another pipeline. We make a choice where to send our data at the beginning and in the middle as well. What happens inside It's pretty funny. You can see some nice animation here. The data comes in, there is buffering, and in each pipeline, actually I show you just one conveyor, right? Just one pipeline. In each pipeline, there are 18 independent parsers, 100 gigabits per second in each of them. Then those packets go to the processing pipeline. And what is important is that those packets only use a part of those resources, those that are designed for input processing. And then this data is bufferized and goes to the output pipeline where there are parsers. And then this data goes through the same stages, but the color of the resources is different. They are light green here. So as a result, our software can be very flexible. Some software can have or needs to have more resources. It depends on the way your compiler compiles this data. But anyway, the program, the software is very flexible. And you can see here that at each cycle, there is one packet coming in, one packet coming out, and the whole device works with two pipelines at the same time. And we have several dozens of packets being processed at the same time. And one pipeline can process up to 720 packets at the same time. There are some other devices here. I'll tell you later about them. One important thing in Tofino is the header and metadata bus, which exchanges all information. And data is put in containers or registers, which can be 8-bit, 16-bit, or 32-bit. In this bus, there's a total of 4 kilobytes. Of course, the young generation doesn't know what is less than 1 gigabyte, so it seems to be little. But just think about Tofino. What is it? It is a 4096 bit processor. So all those 4096 bits are processed at the same time. And we have 224 containers like that. And what happens is that in each container, there is a small arithmetic device or calculating device. Let's look at this input, which works with our headers. You can see that a lot of operations are done in parallel. So if you look at this code, you can see that each line is an operation with a separate code. And what happens here is that each out of those 224 containers has its own calculation instruction. And the instruction is written in BLIWs. They are some long words. There are 224 sections or words, and in each word there is an instruction for a specific computation device. And within each table there is an indicator to a relevant word. And then we use the OR logical operation. And we can fulfill up to 224 operations simultaneously within each cycle. So our frequency is more than 1 gigahertz. So this device really runs in parallel. We also have the match action unit block, which has special multipliers. And as a result, we can do search in a large number of tables in parallel, up to 16. And here I would like to show you a small visualization of what's located inside. There are some multiplexers. One multiplexer uses those decamps or triple tables, then this data goes to tcams, and then it goes to hash bits. This hash device can generate hashes. And then we have the SRAM blocks, where we can put keys, data, counts, special registers, and so on and so forth. Here we have those long words that are instructions, and there is a lot of interesting logic here. For example, these are gateways which ensure special operations such as the if operation and so on. So we have such components in each of the 12 blocks, and it's programmed in the P4 language. It's a pretty simple language which has some data types with which we are familiar. There are bit sequences, there are numbers, and each length in the bit has its own type of data. And of course, there are expressions, there are parsers, and there are standard controlling structures, such as the if operator, the switch operator. We don't have a cycle operator, but those controls are used to run those parsers and deparsers and other elements. The interesting thing is that P4 can support different elements. For each particular microchip, because the manufacturer shows what elements can be programmed in a microchip. And this language also supports the so-called external blocks or externs, which describe different functions which can't be normally described in a language. This is the P4 code. I already showed you one example. There's another example. You see that there is nothing difficult here. In the RFC, you can write your own header. Here you write what fields are used for keys, which fields are used for actions, what the size should be, and what should the default action be. And the action is described as in many other languages. Here you can see the parameters, and here you write what needs to be done. The important thing about the language is that it's not a proprietary language. It's an open language. And I'm a member of the language development group, and it is done under the auspices of Open Network Foundation. And it's all done by the p4.org organization. And here you can see the members of this organization. They come from different places. There are hardware developers, microchip developers, and manufacturers, organizations, and end users. The membership is free of charge, so I invite you to join this organization. We already have some members from Russia as well, and some of them have started looking into it. Here you can see the P4 application areas. One thing that we discussed, that was discussed by Dmitry at the previous presentation, is machine learning, of course. And we also can do different things with P4. Along with the normal routing and switching, we can build smart firewalls or balancing or telemetry, because it's very easy to use interim results and send them from the switch to the packet and so on.
And finally, to conclude my presentation, I just wanted to say that what I would advise you to do. First, sadly, such programmable community has opened a wide spectrum for you. Yeah, just to give it a try, to test. Try doing something. You may use Whitebox and write your own commutator and write your own extension or your own control plane or do whatever you need. Secondly, come to Barefoot Academy, and in 2 actually weeks it will be called Interconnectivity Academy. This is an institution which I'm heading, where we train people to program, and if you're working in some organization, you're invited to join P4 Torque and to do more with the programmable commentators. Thank you so much. Vladimir, thank you so much. We have time for one question only. And I will abuse my role as a moderator to pick one question. So let's discuss what a rookie needs in order to get started. There was a question, advice and AD for a rookie. And software, you can start with VPP or something else. You want just to start from scratch, to start with the simplest thing. Before to Torque, they have a simulator of behavioral model version 2. And this is a software switch. But if you want to start working with Tough-in and really to programming of real chips is different from programming of abstract software switches, because the number of limitations and things you have to know in order to program a chip is huge. What you can do? You can turn to Intel, and after you sign a non-disclosure agreement, and for the research organizations and projects who have our own program, this is for free. When you sign an agreement or a document, then you get an access to emulator of the chip and to the P4 Studio with a visualizer, calculator, and many other things. You can start working with that. And in many cases, you can just buy white boxes with the Tough-in installed, and on top you may actually install P4 Studio, and you can start working with that. So it's not different from just buying a computer, installing Linux, and start working with that. So it looks very much the same. Thank you so much. Please go to our chat. There are lots of questions. Unfortunately, we cannot spell them out. Yes, I saw the flow of the questions there, so let me start answering them. Thank you so much. Announce break until 5 o'clock, when we'll continue with our next speaker. It's 5 o'clock Moscow time and we go on, but actually, we hit a strikeout of the technical glitches. That's why Jeff Tansura presentation would be delayed for undefined period of time. So next, presentation would be led by Chris from Cisco. He will tell us about Ansible and Terraform in the classical networks. There is one more technical thing. Chris has problems with internet connection. That's why what we're going to show to you, it would be the screen test. But the speaker will join us for a Q&A session, so welcome to ask your questions.
My name is Chris Paggen. I work for Cisco as a distinguished engineer in the data center group. And what I'm going to be talking about today is how you can use a tool from HashiCorp called Terraform to automate the deployment of application and network infrastructure. And in this particular instance, the network infrastructure is Cisco's ACI. So ACI is an acronym for Application-Centric Infrastructure, and it is Cisco's SDN solution for the data center. So just as a super quick recap, because I understand that not everyone might be familiar with what ACI is. So ACI is essentially a series of Nexus 9000 switches that are configured in leaf and spine architecture as depicted here, and they are controlled by a cluster of controllers. The controllers are called APIC. APIC essentially abstracts the configuration monitoring of configuration and devices through a REST API and, of course, a user interface, which is actually based on that REST API. So what we're going to be doing here is to enable workloads to communicate on the fabric. We will actually use a configuration management tool, which is called Terraform, to communicate with the controllers so that the controllers can then implement our intent or desired configuration end state on the underlying infrastructure. Now in ACI, you have a series of logical constructs, which are tenants, and inside the tenants, you have group of endpoints, which are called endpoint groups. And then you can apply contracts between endpoint groups to allow communication. So by default, no one can talk to anyone unless you explicitly allow communication between endpoint groups. You can also abstract the connection between ACI and a VMware vCenter server, and the vCenter inventory is then modeled as an object in ACI. What that means is I can then apply the vCenter server inventory, if you will, on the endpoint group, and that will cause ACI to program the vCenter server with a port group and a VLAN for virtual machines to join the infrastructure. So that's super high level of ACI. Just all you need to remember, it's a fully programmable data center fabric, highly scalable and intent driven. So you'll see what that means in a few minutes. So this is ACI. The second tool, which is going to come into picture, is Terraform. Now, Terraform is from a company called HashiCorp, which is over here. And HashiCorp makes a series of tools. One of them is in the area of configuration and infrastructure provisioning and management. So as they describe it here, it's a tool for building, changing, and versioning infrastructure safely and efficiently. It is much like Ansible with a twist, a very big twist. Terraform keeps state. In other words, when Terraform pushes a configuration, it knows what it has pushed, and it can compare the configuration on the device with what it has pushed. So with Terraform, you can always ensure that you have an immutable infrastructure. So what that means is if Terraform realizes that there's too much config drift, it will not hesitate to perform a clean slate reset and reprogram the infrastructure to get to your desired level of configuration. So that's quite different from Ansible, which just keeps adding the changes on top of one another. Also, where Terraform is very, very good is at cleaning up. So when you decommission resources, Terraform is very, very good. It will very easily remove what it has provisioned. So that's why it's getting very popular. Also, Terraform has a series of providers, and providers really mean resource providers. So for example, there is a Terraform module for ACI, but there is one for vCenter, there is one for Amazon EC2, there is one for Azure Virtual Machines, there is one for Kubernetes, and so on and so forth. There's dozens and dozens of modules. So I'm going to be exploring what you can do with HashiCorp and ACI in this little session over here. Right, let's get started. So I'm going to log into my fabric over here. So this is the ACI user interface. The user interface uses the REST API behind the scenes. So everything that you see in the user interface is actually queried from the backend API. You can actually inspect all of that, but that's outside the scope of this particular session. So what I'm going to do is jump directly into the tenants section, and you'll see that you have a lot of tenants. Now, a tenant could be a customer, it could be a department inside a customer. They're essentially units of isolation. So if you look at one of these tenants, by default, if you put a workload into one of the tenants, then they cannot talk to other tenants. Resources are completely isolated. It's stronger than a VRF because there is really no visibility between a tenant and another. You can do role-based access control and make sure that only the admin of that tenant sees that, and the admin of that tenant sees this one. And there's no crosstalk or cross visibility, if you will. So right now there is actually a tenant called Yandex demo, which is from me running the demo while beta testing this, if you will. But you'll see that it's going to get destroyed. So if I look inside the tenant, you'll see what I was talking about. You'll see endpoint groups and the contracts that I was talking about. So let me zoom into the tenant now, so you can see what that looks like. So if I go inside the tenant, you'll see that we have endpoint groups under application profile. So this is just a folder. You can, for example, say you have an e-commerce application or a ticketing system, what have you. And then you have these endpoint groups. This could be like web front end, back end, database, Redis, what have you. And between these endpoint groups, you put contracts that essentially decide, how the endpoints that are in here can talk or be contacted. So you have a relation of provider and consumer in the contract, and that decides, what do you provide as a service and what do you consume. And these are essentially filters that are TCP ports. That's all it is. It's like a stateless access list. It's the same thing. And if I go to EPG2, for example, well, this one provides web but doesn't consume anything. So it consumes default, which is a permit any, but it provides web, and the other one consumes web. So you can see that this is giving TCP/80 and this is consuming TCP/80. Now what I can do, like I was explaining, is in the EPG, I can map a domain, and in this case, this is a vCenter server from VMware, vCenter 7, which means that now this EPG will create a port group on a distributed virtual switch on that vCenter, and a VM can then join that endpoint group simply by attaching to the port group, which is corresponding to that EPG in the DVS. That's not done by Terraform, that's done by ACI talking directly to vCenter using the REST API of vCenter. But here's what I'm going to do. I'm going to go to my vCenter server, which is here. I have a small cluster. I have 2 ESXi hosts. There's 2 VMs. You don't pay attention to them. They're not relevant to this demo. And what I have is the code here that I'm going to use to provision my infrastructure. So this is Terraform. Terraform uses a language called HCL. This is the HashiCorp configuration language. Much like in Ansible, you can have separation of concerns. So you can describe the data and the variables completely independent of your code, which is exactly what I'm doing here. So what I have, I'm going to start with simple stuff. I have a series of variables, which I'm defining in this file. You can also get the variables from different sources, from a dynamic inventory and so on and so forth, from a script, but I'm going to keep it simple and instantiate the variables over here. So for example, I have the name of the tenant, which is Yandex demo, the username and key, which I'm going to use to program ACI over here. Where is my ACI fabric? This is HTTPS 168.221, which is where I was browsing before. And then here I have bridge domain 1 subnet and bridge domain 2 subnet. Bridge domain is essentially the Anycast gateway address that is going to be applicable to an endpoint group. So in my case, I'm going to have EPG1 mapped to that BD, bridge domain, and EPG2 mapped to that bridge domain. Then I specify where is my vCenter object, right? And then what is the name of the object to go to the internet. That's my ACI variable file. Then I have another variables file, which is for vCenter. Now I have my vCenter username and password. I have my vCenter server, SSH user and password. I have a list here of DNS servers. There's only one in the list. There's different data types, by the way, in Terraform. So here I'm using mostly strings, but you have lists, you have maps, you have booleans. So there's a series of different things. And then what I have next is the cluster, the data center, the data store, and a VM template. Okay, so that's essentially my data structure that I'm going to be using in my code. Well, where is the code? Well, the code is here. There is a piece of code for VMware and a piece of code for ACI. So let's start with the ACI bit. The way you access or address an infrastructure provider in Terraform is by using something called a provider. So Cisco builds a provider for ACI, a provider for NXOS, a provider for DCNM, and there's a provider for multi-site orchestrator, and so on and so forth. And VMware will give you a provider for vCenter, and Amazon will give you a provider for EC2, etc., etc. So here, what I do is I follow the documentation, of course, for the provider, and I provide what it wants in terms of minimum required parameters. So here, the username, private key, certificate name, are we using TLS verification or not? And what is the URL? Well, this is coming from variables in the previous file. Now, you may be thinking, how do I link this code and that file? You don't. You just leave it in the same directory, and Terraform will do the necessary steps to essentially combine the inventory, or I call it inventory because I use Ansible as well, but it will combine the variables and that code together. Then I have something called a data source. A data source is an object which exists already, which has not been created necessarily by Terraform, but I want to get a reference to that object because I'm going to be referring to it. I'm not going to create it or delete it, but I will refer to it. That's called a data source, right? So here I'm saying I will use something from the common tenant. I will use something from this internet connection. But then I have another type of object, which is called a resource. A resource is something that Terraform creates. So in this example, I will create a tenant. This is not something you can invent. So the name of the resource actually is, of course, described in the provider. So if you look at the documentation for the ACI provider, you will find that there's a series of resources. There's plus, 150 plus resources. And one of them is a tenant. And I go and get the name of the tenant, and I can put here a description, right? There's more attributes, and you have to go back to the provider to find out what those are. Then we have a VRF, and you can see here that I'm referring to the previously created resources ID. So I have ACI tenant, which is a type of resource, .demo, which is here, .id. This basically says create a VRF in that tenant. Then I have a bridge domain number 1 and a bridge domain number 2. And again, I have references to the tenant and reference to the VRF now. So you can see that this is a hierarchical object model. So it's like a configuration tree. You can think of it as at the top, you have the tenant, then the VRF, and the VRF has optional children called bridge domains. That's exactly what I'm doing here. Then in the bridge domains, I have the subnets. So you can see that the subnet is referring to the ID of the bridge domain. In this case, bridge domain 1, in that case, bridge domain 2. And then I have something pretty cool that I wanted to show you. In case the object that you want to manipulate, imagine there is no resource for it. You go, I want to do something, but there's no resource that Cisco has provided yet for that. Am I stuck? No. We have a generic resource called ACI REST. And that essentially is an interface to the APIC controller's REST API. So you simply give the path, and you can use variable substitution in the URL and in the here text, like so. And it will then post this payload at that URL. So this is a raw interface directly into the REST API. So that's actually very cool because you can then do whatever you want in Terraform, even if there is no object for what you want. Then I have my application profile, my data source for vCenter, and then EPG1, EPG2 down there, and then the domain. So I'm mapping my vCenter to my EPGs over here, and then I'm creating the contracts, right? The web contract, the default contract, and then my filter. See, allow HTTPS, allow ICMP, and which port am I using, and which protocol. That's the code. This is the HCL for ACI. And then I have the same thing on the VMware side. So now you see that the provider is vSphere. So it's slightly different. And what do I have? I also have a bunch of data sources, the vSphere data center, the data store, the DVS, the two networks that ACI is going to push on that DVS, if you remember. So I'm referring to them as data. So I don't create much here. I get references to these objects primarily, right? I have a VM template over here. I have a vSphere cluster, right? And then I have local variables. So these are essentially used during runtime in this specific HCL specification. And what they are is they're, you can think of them as dictionaries, if you know Python or JSON objects. They're very similar. They're called maps in HCL, but they're exactly the same thing, right? They're basically a series of key value pairs over here. It's kind of a list of a key value pair system. So I have a port group map, an IP address map, a gateway map. So you see here VM1 will have a specific port group, VM2 will have another port group, VM1 will have this IP address, that IP address. I could move this into variables, of course, right? Because I'm doing it here. So I could move this into the variable file and have absolutely no hard-coded values in my code. And then what do? Well, I create, the moment you see resource means create, I create two VMs. I have a loop. The name will be the prefix plus the count of the current iterator. So VM1 will be 1 and then VM2 will be 2. Where do I create it? How many CPUs and how much memory and so on and so forth. Network interface, and you see that I put the network interface in the port group that I want. Right? Then I customize the host, I assign the IP address to it, and I'm pretty much done. What I can do, which I'm not showing here because this is an introduction, so I'm not going to go super deep, but what you can have is something called a local or a remote provisioner. So you can use Ansible either locally on the control machine to run a playbook against the VMs that you created, or you can use a remote provisioner. And that can be just a shell script if you want, or Ansible as well. So if you have Ansible installed in the VM, you can then copy a file using Terraform. You can go get a file, put it in the VM, and then run the Ansible playbook on the files that you copied. So you can use Terraform and Ansible. It's actually very common to do both because Terraform is very good at provisioning infrastructure, and Ansible is very good at configuring applications and things of that nature, which you wouldn't necessarily do with Terraform. All right, so enough talking from me, and I'm going to get started on this. So to give you an example, what I have is a little script here which runs the demo, right? So I go to the VMware directory, I will destroy whatever exists, I go to ACI and I will destroy my tenant, and then I will wait for input, and then we'll do a Terraform plan, and then we'll apply it. All right, so I'm going to get going with this. I'm going to start the script, and then we'll go take a look at what happens on the ACI Fabric and on the VMware side. All right, so I'm in the directory where you have the script over here, and if I run the script, we'll see what happens. So now it's going to go into the VMware folder, and it will destroy whatever it finds. Now it's going to go on ACI, and it will compare the plan that it has with the actual configuration. And it says, okay, I deleted 19 resources. Well, let's go take a look if that's true. So if I go here now, I go in my ACI Fabric. If you remember, we had a tenant called Yandex demo. So if I go here, it's gone. The tenant is completely gone. So it destroyed the tenant. Okay. On vCenter, it didn't do much because there was nothing. But let's go and continue our demo. I will say continue now. And now it's basically telling you I'm going to add 19 things on ACI. Really? Well, let's go see Yandex. So now you see that something is coming up with the name Yandex demo. And it tells you this has been created from an orchestrator. Only make changes from the orchestrator. And you see here EPGs, bridge domain, VRFs. Look at the IP addresses for the bridge domains, for example. You know, in BD1, I have 1111. In BD2, 1121. Exactly like my plan, right? So I have my two EPGs over here, and they have the contracts that are defined in the code. They are mapped to my domain. And if I go to EPG1 now, and I look at the operational angle over here, I do not have a VM yet in here. There's nothing yet. Well, that's because Terraform is busy creating the VMs. Now it's creating a virtual machine. So if I go here, you see here that it's spinning up two VMs. So I'm going to give it a couple of minutes. So now the Terraform provider is taking care of powering the VMs. And if you look at the VMs, you'll see that they were placed in the right port group. So VM1 is in port group 1, and VM2 is in port group 2. Right here, right? And again, those port groups, they were pushed by ACI on vCenter, so right there. And they're backed by a specific VLAN. So if I look over here, for example, and you look at the settings, you'll see that there's a dynamic VLAN which was pushed. And ACI takes care of enabling the VLAN on the interface where the VM appears. So it's actually pretty efficient in terms of resource provisioning itself. So now that I have the VMs created and attached and powered up, if I go to ACI and I go to my endpoint group, you see in each endpoint group the VMs coming up. So if I go to EPG2 and I go to operational, you see that I have 112.100, and in this one I have 111.100. And now, of course, what I can do is go to the VM, and in this case, you know, they're very basic VMs, right? But I could have deployed a complete application. And what I'm going to do here is just log into the VM and do a ping, and we'll see if that works. So I'm inside. I'm on the console. So I just log in. And you see that my address is 111.100. So I can ping my default gateway, which is 22BDF8. That's basically the ACI bridge domain. So if I look over here, you'll see that 22BDF8. If I go to operational, I'm sorry, if I go to policy, L3 out, I have to go here and go to policy and go over here. I'll have the MAC address. So that's it, right? So if I go to the VM and I do IP route, my default gateway is the ACI fabric. And if I go to 100, well, I can ping the other VM. So you see, without touching a line of command line, I can deploy complete applications and the required network that goes with it. But here's the cool bit. So if I go to ACI now, imagine I made a mistake in my subnet. I can go back here, go to my variables, change it to this. Imagine this becomes 200. You save this, you go into the directory for ACI, and you can interrogate Terraform and say, please compare what I have here with what is on the device. And now it's essentially comparing its current state with ACI, and it will tell us, well, I have to change a few things, 3 to add. And it says, what you want here, which is a new subnet, forces a replacement of the subnet, but the rest is not touched. So it will tell you, everything else, he won't touch. Of course, he's going to touch the ACI REST, by the way, because anything which is directly interacting with the REST API, Terraform doesn't know the state. The good thing is the REST API on ACI is idempotent, which means that if I push this 1,000 times, there will be no change unless I really change something. So this is harmless. But Terraform says, the rest I'm not going to touch, just the subnet. And then you can essentially go and say Terraform apply, auto approve. And now watch this. If I look at this subnet, so keep your eye on this field over here, and you'll see that within a few seconds, the subnet is going to change. You see here, that was Terraform. And I can change it again and again and again and again. And if I add stuff myself, or if I remove stuff, it will tell me, well, look, this is deviating from the configuration that you wanted. So that's in a nutshell what Terraform can do with ACI and vCenter in this case. We just scratched the surface. There's a lot more that you can do with Terraform and ACI, of course. And I encourage you to watch other webinars that we've done and white papers and demos. And I hope this was helpful. So thank you very much for watching this.
Great. Hello.
Hello.
How are you?
I am good, and you?
Yeah. Okay. Thank you for your introduction. So we have several questions and a few minutes. One second. Sorry. Could you please tell us about some open source alternatives for Cisco ACI? So, as example, I'm working in rather hyperscaler company, so I want to use several vendors. So, what should I do?
There's two different questions. One is, do we have open source alternatives? And I want to use multiple vendors. So open source alternatives in the area of data center fabrics, there's not much choice, because you're going to have to buy the hardware inevitably, and that kind of limits the choices you have. So there are programs out there where you can buy just the sheet metal, essentially just the switch and the ports, and a very basic slice of software on top of which you can install your own software. Cisco has a program actually which we don't market very aggressively because it's for a very niche market, but we have something called Sonic. So if you want to know more, we can talk about that. So that's essentially Cisco just selling you the hardware without the software, and then you can install something else on top. There is that option. There's other options out there. If you look for white label boxes or white label solutions, you will find something. They're not very popular unless you are a massively scalable data center and you have the engineering know-how to build and maintain a solution like that. So in the enterprise, in the financial sector, in the industry sector, we don't see that kind of solution. But again, if you are a Google-like company, that might work for you. That's
So am I right? Is it possible to connect Cisco ACI and some open source solution like Sonic? Is it possible?
Well, Sonic is not ACI, right? So Sonic is its own program.
Sure.
Yeah. And yeah, I mean, you could use Sonic and connect it to something like ACI or Juniper or Arista or whatever you want. You will have, as usual, right? If you take systems from multiple vendors, it will be the lowest common denominator that will dictate what works and what doesn't work. So typically, every vendor will give you an RFC compliant implementation of BGP, OSPF, ISIS, VXLAN, and that's going to work. But you will have the basic functionality because it's always the same, right? I mean, a commercial vendor wants to differentiate what they sell you compared to a competitor. So, every vendor will try to add a little bit of something on top of the plain RFC version. So that's what you're
Fair
going to
enough.
have.
Yeah, fair enough. Okay, so next question. Is any API exist to automate resource creation?
The resource creation in Terraform or on ACI? So yes, I think I understand the question. So if the question is, I would like to automate all of this, the HCL creation and trigger plans, being applied and destroyed. Yes, there is something called Terraform Cloud, which is provided by HashiCorp, which has an API, and you can actually trigger HCL plans using the API, if that's what you're asking.
Yeah. Thank you. So we should move forward. Please join our Telegram chat and talk with our members. Thank you.
Thank you.
Итак, дорогие зрители,
Dear
следующий наш
colleagues,
доклад,
our
он будет
next
как раз немножко
presentation is about
Как вы знаете,
the world of open source. As you know, right now we have very popular open source solutions for switches, such as Sonic from Microsoft. And of course, there's also a Linux switch, which was actively promoted by Neonox earlier, and which is promoted by another developer right now. And we will now hear about the experience of using such solutions. Alexander, you have the floor. Hi. I'm going to try to get connected to you now. Okay, I'm ready. Can I start? Yes. You are on air. You can start. Good afternoon. My name is Alexander Zubkov. I work at Bottle Labs. And today I would like to introduce you to our Linux systems. Here's what we do. We use Neonox. We use buy-box switches. These are switches which can use different operating systems, SDKs, and those operating systems are interacting with those things. And we also have a system from Neonox that supports those switches. There is also the system of High SDK, which is available. And also, it's also supported by Silo. This is an attempt to do SDK for different switches, which are used in the Sonic system. So this is the infrastructure which enables you to build this application by means of the normal system settings. They are the switch settings, the so-called offload. And on this picture, you can see the commutator drive, which is in the pink color. Dear colleagues, it seems that we have some technical issues and we are trying to solve them right now.
Well, while we are addressing technical glitches, let us tell tales and let's announce a contest for telling the reason why this happened. I'm reading from the chat. So, Chinan has come. No, this is not very funny. Segment routing, V6. That's better. So the routes failed. So BGP, VCF. Let's move forward. Let's blame that for Wi-Fi 2.0 VPN. COS is not needed. I support we don't need COS. Flow label would be handy. So first it gave a WIMP, then it was all over. Telephony is bubbly, and you do know who is to be blamed for that. PSET actually did not provision. No one is cracking joke that we have already started. We're speaking about distribution. Sounds good. Mellanox got restarted. So we are not in Mellanox any longer. Ilya. Right, probably you launched my script about Cisco ACI. The nodes would be switched. Yes, we're doing that. We are switching the nodes. DDoS attack against the Qrator. I don't think that this is realistic. Engineering writes that internet is down. Yes, probably that's possible. Cable is crippled. Why not? Other assumptions. What could have happened? There are no more options. Okay. I apologize. Actually, everything was down from my side, but till now we're joined by Alexander Zubkov, and we'll connect him in several minutes. When you lost me? I think we lost you from the very beginning, so I suggest that you start from scratch. Sounds good. Sasha, let me introduce you once again. Sasha is from Qrator Labs, and he will tell us how to live with Linux, Switchdev, with Whitebox, and over to you. I'd like to tell you about Linux Switchdev, what this is about, and how we are living with that. We're using Switchdev with Mellanox Qrator, and they are attributable to white box switches, so it means that you can install different operational systems on that commutator, and usually the vendor would offer certain SDK for that, and switch abstraction interface to interact with the commutator. There is an operational system from Mellanox, and it's been supported by SAI, some common languages for different commutators. They have Sonic, and it's been supported by Sonic Switchdev. Switchdev is a kind of infrastructure in kernel infrastructure, which helps you to display the in-kernel infrastructure and install that on the hardware of your commutator. And on the slide you may see that pink stands for the commutator, blue stands for the AP, and utilize for setting of the user interface. Yes, Switchdev is the mediator between user space and the kernel, and It provides infrastructure for the kernel to display that. Linux commutators are using a standard set of functions, so routers, HCP, etc. So these all things have been supported. And you may offload the data plane. That we are lacking policy-based routing. So there is no support of the offload. Linux driver may be found in the vanilla kernel version, so you don't need any patches or any drivers. You may take the kernel from your distribution or compile that yourself. Some of the features are updated by the driver itself. In order to tune the switch itself, certainly we use certain utilized standard ones available from Linux Toolkit, HTool, LLDP, QoS, and Cisco for certain parameters. For VRF, Linux has their network expressors, and there is a subsystem of VRF which is different from the rest of the system. Your interface is allocated in one X space. So in case you're working with the VRF, in order to manage the routing, you have to develop a special rule, IP rule, which defines what VRF this or that package is attributable to, and actually it would send that to a special routing tab. Special interface, VRF interface would be set up, and the tab would be connected to that, or pegged to that, or linked to that. If you want to add one more interface to your VRF, by means of an IP link, you will set master for your interface. So how, as far as these interfaces are located in the same environment, there is an opportunity. You may indicate a route from a different VRF and provide for the communication. For instance, we have the following issue. We get traffic from sublink and would like to direct that to some filtering nodes. In Cisco, we would develop an IP policy roadmap, or we would set the next hop. In Linux, actually, it is not all reduced to IP rule, and we made the following thing. We have divided the VRF into two parts. In one part, you may find some external interface, and in the other part, you may find the interface with our filtering nodes. This is how it all links. This is how the routing looks like. In the internal VRF, actually, you have a standardized route, domestic routes and default route from our link. And in the outside, external VRF, actually, you may find the filtering nodes. So it's kind of a pseudo or quasi router. In general, when you are configuring your commutator, you have to set the ports, then you set the bond, then bridges, then VLAN, loopback addresses, and the routes. Usually it's been driven by the very structure of the interfaces, where there might be more restrictions. That's a very boring piece of labor. Before, we had a big script which would set these things, but sometimes we have to introduce some runtime changes. And this causes pain because you have to actually disassemble that starting from the interface, and this is pregnant with mistakes. fraught with mistakes. You change something and the environment would take care of that. And this is a low-tier work being done. But luckily we have Perl, and we have designed a router, and it is being used in order to generate the instructions to set the network. And also we support the changes. So once actually certain pushes are being made, you may have a look at what can be done in order to bring that in compliance with your desire, with your intent. Initially, once you launch that configuration, so the system will generate this set of commands. And there might be different commands, but if you are not using that script, then actually it can be supported. For instance, once you have to take one port and switch that to another port, then you have to switch this port off the previous bond, and the bond has to be disconnected from the bridge. Then actually the bridge has to be changed, and the bond has to be reconnected to another bridge, and it's very boring to be done manually, and the script does that on its own. Next. ACL, which you have to set on your own. APL actually is being used for filtering. If you actually want to do the filtering in TC, you have to use special switch filters. You have to bear in mind that these filters actually are going to filter not the routed traffic, but also the one which is commuted. And actually it can be connected only to the physical ports. If you're working with VLAN, then more sophisticated approaches are needed. And there are some very interesting features. For instance, you may put a block on top of your interface on several interfaces, and they would share common filter. There is a go-to operator, which is quite good. And you may do some linear connections. We have a special Utilite XSL. We mainly are working with VLAN at such a tier, at such a level. And for every VLAN, it creates its own chain. And in the main line, it would match the VLAN and would move to another chain. This is a case of such a configuration. And as a result, we get such commands. They are less in number than a case of configuration, because one rule stands for one command. But if you have to introduce certain changes, then there is another Utilite, which makes sure that all the changes are being redone, especially the ones which are amended or changed. And the enumeration would change so that the reference is made to the new chain. Obviously, if you do that manually, then it would be enough to write one command, but for that you actually have to look at the current state. And this is how TC filter looks like. And it's very difficult to work with it. You're working with it and people would just pass by and looking askew at you. ACL filter was the first to be developed by us because actually it was much easier for us to start working with that. This Utilite is published in the public domain, so it's free. You may use MIT license, so with no guarantee, certainly, no warranty, and you will get a couple of scripts, quite little scripts with no dependence, so they are using a couple of per modules, and Linux Utilites are to be used. And finally, for those who have some experience of working with serial console tips, if you think that this is actually a way out of Vim, that's true. This is a command for BIOS, which actually equals Control Alt Delete. For instance, if the computer has frozen, you can take advantage of that. And, your kernel has to be controlled from another space. Otherwise, it would be very difficult to reset the switch. And when you're working with the hardware and with regular terminals, you're using print screen, and you will have to send a special break command. And you will have to use a special key in order to get to BIOS when booting and rebooting your computer. You may press Ctrl B key. Thank you so much. This is what I wanted to tell you in brief, in a nutshell. Should you have any questions, you're most welcome. Thank you so much for your presentation. Look, there was the following question. Why still you opted for Perl? Just I like it. I know Perl better than anything else. It depends. I think that the question would be what can be done faster in order to do that quicker. Probably we will rewrite that. So there was an expertise, actually, and it was easier for you to do that in Perl. Tell us, is there any CI/CD infrastructure around that? How will the whole package be assembled? The system package? Well, you should have some systemic kernel, some packages. How do you build the whole system? Well, in that case, this is a kind of an operational system. And there is a BOR daemon, and there are no any objectives which have to be addressed from that. We're using a template. Okay. Just give me a minute. I will look into the chat. Probably we have some questions from there. No questions. Please join our chat. Should there be any questions, they will emerge there. And let's move forward. The contest which I have held, we have chosen two winners unanimously. The first one won according to the final score. Anton Klochkov. Anton, what's the size of your T-shirt? And we'll think something out. And the second person, who we liked very much, is Oleg Sidorkin. I liked very much the option, actually. The dog mounts on laundry machine has arrived. Let's move forward to our next presentation. Would be the last one, I hope. And it will be about automation. And MTS expert from will tell us about that. He will tell us about the ISP automation and plans for the future. Vadim, over to you.
Hello, thank you for joining the Yandex 2020 conference. My name is Vadim. I am a network architect at MTS, and today I'm going to tell you about our tasks as a network operator, the challenges that we are facing and our current solution, and other processes which are connected with network automation. We have a multi-vendor network which consists of Cisco, Juniper, Huawei, Nokia, and we also have a large stack of protocols. Our main goal is service automation. By services, I mean automation of business processes in order to be more client-oriented. I'm talking about a connection of B2B clients, and to automate our services, we need several stages. Stage one is document management standardization, which is a complex and important task because we need to standardize all the document operations. The second level is automatic control of a network design. Before changing configurations automatically, we need to learn how to read it and compare them with template parameters. The third phase is migration. The fourth one is automatic testing, because changes in any designs, templates, rules, or equipment should be tested automatically in a lab. And then we have automatic changes in the network. Before automatic changes, we need to carry out semi-automatic changes in order to minimize risks and avoid mistakes. And then there is an important stage, that is integration with internal systems, because the operator already has different systems, and we need to integrate these changes with the existing systems. And after that, we are ready to automate this service. Let's look at a general solution architecture. It's not very different from basic examples or common examples, but here I can identify some commands and 4 different levels. The first level is the network level, with our existing network, which is the responsibility of a network team. The second one is the orchestrator team, which provides information to the network, controls change in it, and is responsible for changes in the network. For example, VPLS and others. And this level provides the KPIs for higher levels. The orchestrator team is responsible for development of common services. And there is also a network automation team, which is responsible for automating networks. There is also another element, which is the foundation for automation, because it's responsible for processing the networks of a particular operator and using this network's resources. Right now, we are working with this network by our own, and we have different systems. We also have the system for template storaging, and we have the NPM. This is System Performance Manager, or NPM. We also have the IPAM, that's the system for running IP addresses, and the doc center is the center where relevant documents are stored, such as designs, rules, algorithms, and templates and schemes used at the network. And then I will tell you more about our services. On the fourth level, there is the service action level, which is responsible for working with clients, and it also has a backend, which is responsible for other things, and there is also a service engine, which gives you user authentication, login, and it ensures security procedures. And this service also automates the workflow. Before implementing this solution, you need to understand that automation is a certain process. This slide shows different levels with different commands. For example, there is the network automation team, which is responsible for automation of the network. And it's very important that all the teams work together, which is why I would like to talk about a new operator, that is service support. Of course, it's important to implement and install the necessary software, which is why you need to have several zones. There is a development zone, where software is developed and debugged. The tester zone and the productive zone, the most responsible one, that's when the software starts working on a real network. And along with the server and network resources, it's important to work together with vendors. And right now we are piloting these solutions together with our partners. And we started by preparing documentation. It turns out that it's very difficult to manage documentation. It's hard to agree on changes in it, which is why we decided to move towards the so-called Jinja 2 format. We create special changes in the GitLab, and then those changes are approved by different departments by using merge request. And then those changes go to the documentation center, and they are accessible to users. As a result, we would like to meet the following requirements to documents. Support of the relevant version. All employees working with the network can get relevant documents on a centralized basis. We can control who changed what and when in the documents. We use machine-readable formats. This is important because, unfortunately, with time it becomes very difficult to check PDF documents, which is why we move to a machine-readable format. A centralized data source. We use a lab and a breakdown format, and as a result, we have a site with relevant documents, and several developers need to work on documents together, and our current format allows it, and we also want to control access to documents. As I mentioned earlier, we need to check what's happening in the network right now, which is why we focused on reports about design deviations. And we started to put together a database, and we are having a special project in order to collect the necessary information about the network. Here you have information about ports, interfaces, services, devices, scaling, parameters, and so on. The important thing is that we started storing all the information regarding different vendors, and we can take an overall solution regardless of the vendor as a result. You can tell me, but Vadim, this is a normal system which is implemented by many different companies. Yes and no. Yes, it's a multi-vendor system. Right now it has 5 network vendors, 3 RLL vendors, and it meets our needs in terms of data processing. It's integrated with our systems at the company. And since we developed this system, we can change the functions easily in it. And right now, this system is a key component for implementing this network in the future. I already mentioned that we are developing a process for running templates. They are located in the gold config system. At the beginning, we need to prepare the input data. It can be a form on the website or something else. And then we need to prepare a configuration template. For that, I only need 7 parameters: region, vendor, device type, software, hostname, loopback, and NNI. I send those parameters to a generator, which sends a request to the database that stores all the parameters. And then a data set is formed with all the parameters. Then this data set is sent to Jinja 2, and then we have a configuration that could be tested automatically or sent to the user. As we work with templates, there are different variables which need to be identified, which is why On this slide, you can see examples of those data sets, how they are written for different equipment. As a result, it's much easier to maintain this system. Another template problem is that templates are very different. You need to be able to choose a template depending on the type of the vendor, type of device, software version. And we resolve this problem by storing the templates in NetLab. And then we store variables based on the connection principle. That is, every variable is linked to the type of region, type of vendor, and so on. This slide shows different variables for the Huawei vendor. The data is collected in the config database, and as the generator sends a request, the variables go back to the database and form a data set that you can see on the screen. And then this data set is sent to the Ginger2 template, and a configuration is formed there. Look at the description field. This is how we link this system with other systems for automatic checking. As a result, we control the variables, we manage the input data for the equipment, and we prepare configurations and templates. As a result, we implement the standard approach to variables in a configuration. We have the master system. There is not much complex logic in those templates. We avoid variable hard code. Our variables are stored in different levels, and we also ensure the generation of configuration. Everything I mentioned today is used successfully in order to automate a service. In our case, I'm talking about the automatic integration between the network and a node, which means that as soon as a node is connected to the network, there is magic. The node is switched to the network automatically. But for that, several stages need to happen, such as network planning, assembly, and switching of the new equipment, the automatic setting of the new node, resetting and testing. Let's look at this process. As we plan a new node, our variables can be chosen at zip engine. I'm talking about different parameters such as the region, name, like for configuring new equipment. At this stage, we also add network DBs, we add new ports, and then we send a request to the orchestrator. And the orchestrator should reset the network. And we use the existing nodes in order to set up the interface, and then we are waiting for the new node to start working, and we check whether it has appeared. After the new device is connected, the orchestrator sets up the new node, then it reconfigures the existing nodes, and then the orchestrator tests the new node, and we have an automatic node which got automatically connected to our network. Right now, we are getting ready for implementing this node in the network, and in the fourth quarter of this year, we are going to implement this system. To conclude, we need to automate our services, and for that purpose, we started additional services such as documentation center and others, and we are ready to launch several cases, and I hope that we will succeed in the future. Thank you. Any questions? Thank you, Vadim. There are a lot of questions, as usual, because this is a very interesting topic. So we have enough time. We have the first question from Roman. What's the configuration of the workflow and what engine do you use? Well, the workflow is implemented on the free work from Apache. I can tell you more about it elsewhere. Right now, I am focusing mostly on those services that need to be automated. At the ISP systems level, well, this level is developed by professional developers with various solutions. I'm not familiar with their architecture, but I know that an Apache solution is used. But my presentation focuses on what communication operators need before automating their network. And that's what I said before. Thank you. The next question. Do you use Cisco solutions in the automation stack? And if yes, how do you integrate them? Yes, we are piloting the Cisco MSO product. Before that, we looked into other systems, but we chose the Cisco system, or the Cisco orchestrator, and we are now using it as a system to get relevant data from the network. And it also ensures the service logic of a network service. That is, it's fully compatible with the equipment, and it is fully responsible for that equipment. So we gave that function to the orchestrator, but the entire logic has been moved to a higher level. All right, but did you want to write something of your own here? Answer, well, initially, yes. But practice shows us that at the beginning it seems to be quite simple. But as soon as you start going deeper into the vendor stack, protocol stack, and you have to write a lot of things, you have to study very thoroughly many other elements. One vendor has 5 of those elements at one company. That's what we've been facing. So in principle, it is possible to write an orchestrator, but at what cost? So we have chosen another approach. We decided to outsource this level to those who do this professionally, who have a lot of experience, who have been around the block. Thank you very much. 1 second, please. So how do you test the configuration? Do you have a pipeline? Well, that's a good question. I got it. Well, look. Let me show it. So what stages do we have when testing? We have the world config system, which contains templates. So we go through this workflow, and we put the templates into here, and we know how to generate them. It all goes very well. And then we submitted the parameters of what we want to generate here, for example.
So that means that we generate the configuration, so we go step by step, hop by hop, and when we get the clear text of configuration, we have data about the type of the text. We see the configuration on the screen. We can see that where we may automatically send a questionnaire to the Palm or use any other methods. Put that into the box, get a feedback from it to understand what actually is there, what is not there. And this is how we check the templates. So in future we have plans for more sophisticated configurations with topologies, etc. But at the moment, we are focusing on the generation and just checking how the configuration is built. A question from Rosa. The template describes the configuration of the node. How the services actually would be described? Look, actually have to divide that. I wanted to include that into the presentation. You have to divide the network services, differentiate between the network services and other services. So the basic station service includes the setting of the port, setting of DRF. This is something you have to actually split and to implement step by step. I've drawn an example again of the configuration. When we have some typical templates for vendors, they are agreed in terms of the providers and support. And then, proceeding from these right templates, we would build the services which are actually define the business logics. And we store separately something for the network and for the business logics of the service. Next question. We are still not out of time, so Vadim, stay with us. Yes, I'm ready for that. Who is used as an orchestrator? Anton asks, how config actually has been flooded through the existing network or not? This is about the delivery method. Unfortunately, well, I don't think that the operator could not afford out-of-band management because it would be a simultaneous network. Therefore, we are using just fallbacks. Okay. And that's why actually I would like to stress that this part of the productive area is very important because, God forbid, we lose something there. That's very important. My question, can you make commit confirmed or not? Well, this role is being played by an orchestrator. It has to identify that moment, but it will not allow for commit. If something goes wrong, actually, it will just abstract the commit. Question from Rosa about the change of the template. Actually, will it be replaced or substituted with the protnet? Actually, we're thinking about that, but we're not ready for that, because this route is quite long, lengthy, and again, from the very beginning, I said that you have to go through all those processes. So once we actually got through there, when we change the documentation, then you have to make a report, and you have automatically either to manually bring the network to what we have changed and move forward. From bottom up, through the same workflow which merges in the configurator. Before that, this was not the case. Next question. Do you deploy the virtual topology of your networks? We'd like to do that, but unfortunately, first of all, the vendors who are supporting the virtual environment, Jupyter, Nokia, and Cisco, they do not allow for costs, and there are some vendors which do not support VMs, and this is a disadvantage for them, I think. In that case, actually, we'd like it to be, but not. No. Okay. On that slide, I would like to highlight lab devices. For the operator, the new feature would be about actually maintaining a lab with all hardware toolkits so that you could check whether T is changed or plates are changed, or chips are changed. And that's why you have to have a lab. The network diagrams, are they used and are they updated? Yes, really, we store that information in the network DB. And there are special interfaces there, and we have an opportunity to get the topology. And most importantly, we can somehow reconcile two nodes. And this is rather important in terms of controlling the configuration. We may check the VDP and radio relay is also the case. And HTA network actually has the same feature. No one actually can move the relay and other systems into the same logics. Okay, Vadim, thank you so much. Okay, answer the questions on the chat. Thank you so much for your answers. And really, there are more questions. And visit our chat and answer the questions. Thank you so much for the presentation. It was really very interesting. Thank you for coming. The feeling is mutual. Bye. Unfortunately, for technical problems, Jeff will not join us. So let's call it a day. And tomorrow, you will get a feedback form. Please fill it out. It's very important for us, because we'd like to hear your feedback. We do want to know what was good, what was not so good, in order to become better for the next year, to select even more interesting technological content for you, in order to make our conference more open and more interesting. We are done with that. I'd like to thank the soft school Inna. Thank you so much. You are our heart. You are integral part of that, and I'd like to express my gratitude to Sasha Azimov, Lisa Gor, Klimenko, Boris, Khasanov, and the program directorate, including your obedient service, Andrei Glaskov. I'd like to thank Marat Sivgatulin and the whole Link Me Up project. Guys, thank you so much for supporting us. I hope that next year we'll see you again alive. Next Hub 2020 is over. Thank you and bye.